Have you ever looked up at the night sky and wondered what our stellar neighbors are really like? Not just the stars we see twinkling overhead, but the ones closest to us in the vast ocean of space beyond our own sun. What's out there? What kinds of stars are near us, just past the edge of our solar system? Are they quiet, strange, dangerous, or maybe familiar in ways we didn't expect? The space around us isn't empty. It's a neighborhood filled with stars, systems, and unseen worlds, each with its own story written in light that has traveled for years just to reach our eyes. Within just 16 light years, about 151 trillion kilometers, there are around 50 star systems. Most of them are dim red dwarfs, invisible without a telescope, their faint glow barely penetrating the darkness. A few are paired together in slow, graceful orbits, dancing through the void over the course of decades or centuries. Some are so faint we didn't even know they were there until recently, hidden in plain sight all along. And scattered among them are planets, some small and rocky, some too hot or too cold, and a few that sit right in the zone where water could exist, where the temperature is just right for oceans to form and persist over billions of years. We'll visit these nearby stars one by one, starting from the sun and heading outward, step by step, deeper into space. We'll stop by Proxima Centauri, just over 4 light-years away, with its Earth-sized planet caught in a dangerous orbit around a flare-prone star. We'll pause at Alpha Centauri, a double star system that feels oddly familiar, like a reflection of what our own solar system might have been under different circumstances. We'll pass rushing stars like Barnard's, quiet loners like Wolf 359, and bright giants like Sirius, each one a different chapter in the cosmic story. Each stop is a different kind of star, a different kind of story, some with planets, some without, some still waiting for us to understand them. It's a short journey by galactic standards, but every step takes us farther than we've ever gone, pushing at the boundaries of human knowledge and imagination. Let's begin where everything begins, with our star, the sun. A fiery light breaks through the edge of the world each morning. It's the sun, the only star we've ever touched, the only one we've truly studied up close, and the only one that's given us life. This is where our journey begins, in the warmth and light that makes all earthly existence possible. We often forget that the sun is a star. It doesn't feel like one because it's so much brighter than the stars we see at night, overwhelming in its brilliance. But that's only because it's close, extraordinarily close, at least on the scale of space where distances are measured not in miles or kilometers, but in the time it takes light itself to travel. The average distance between Earth and the sun is about 149.6 million kilometers, a number so large it becomes almost meaningless until you try to put it into human terms. To put it into perspective, if you could hop in a car and drive straight to the sun at a steady 100 kilometers per hour, never stopping for food, sleep, or fuel, never slowing down for traffic or obstacles, it would take you about 170 years to get there. Think about that for a moment. You would need multiple lifetimes just to drive there at highway speed. A commercial airliner flying at around 900 kilometers per hour would take roughly 19 years, nearly 2 decades of constant flight without landing. And that's just one way. The scale is massive, almost incomprehensible when we try to imagine it in terms of human travel. And yet, in the language of astronomy, this distance is considered small, local even. Because the sun is so close compared to everything else in space, scientists gave this particular distance a name: 1 astronomical unit, or 1O. It's become a kind of ruler we use to measure distances within our solar system, a baseline that makes the vastness slightly more manageable. Mars is about 1.5 astronomical units from the sun, orbiting in the cooler outer regions. Jupiter is about 5.2 astronomical units, a gas giant circling far from the sun's warmth. And Pluto, that distant frozen world at the edge of our planetary system, sits roughly 39 astronomical units away, where the sun appears as little more than a bright star in a black sky. Every planet's orbit can be measured in relation to this one fundamental stretch of space between us and our star. It's a baseline, a yardstick made from sunlight, a way of making sense of the cosmic distances that separate the worlds of our solar family. But of course, in space, light doesn't just bring warmth. It brings time, and with it, a strange sense of delay that reminds us that even at the incredible speed of light, the universe is vast. Light from the sun travels at nearly 300,000 kilometers per second, faster than anything we can build or imagine. Even at that incredible speed, it still takes over 8 minutes, specifically 8 minutes and 20 seconds, for that light to reach Earth. That means when you step outside and feel the sun on your face, you're feeling something that happened 8 minutes ago, a ghost of the past warming your skin. If the sun were to suddenly die out right now, winking out of existence in an instant, it would still appear to shine for at least 8 more minutes before we'd even know anything had happened. We would continue in blissful ignorance, bathed in light from a star that no longer existed, until that final wave of photons arrived and darkness fell. The sun is not just a ball of light in the sky. It's a complex, dynamic engine of matter and energy, a fusion reactor of almost unimaginable power. And more than that, it's our reference point for understanding all other stars. Everything we know about stellar physics, stellar evolution, stellar behavior begins with understanding this one star. It's close enough to study in extraordinary detail, and from it, we've learned the basic vocabulary of stars. Their structure, their behavior, their life cycles, the way they're born and the way they die. The sun is our first language in the universe, the Rosetta Stone that helps us decode all the other stars we see scattered across the night sky. At the very center of the sun is the core, a region of such extreme temperature and pressure that matter behaves in ways we can barely replicate on Earth. You can think of it like the engine of a car, except unimaginably hotter and much more powerful. In this core, temperatures reach about 15 million degrees Celsius, hot enough to overcome the natural repulsion between atomic nuclei. The sun squeezes hydrogen atoms so tightly that they fuse together and become helium, releasing tremendous amounts of energy in the process. This process is called nuclear fusion, and it releases enough energy to light up everything you see around you, to warm the Earth, to drive our weather, to make photosynthesis possible, to sustain all life as we know it. Every second, the sun fuses about 600 million tons of hydrogen in its core. About 4 million tons of that mass gets converted directly into energy, vanishing from existence and reappearing as heat and light according to Einstein's famous equation. That energy then begins a long journey outward through the sun's layers, eventually reaching us here on Earth, 93 million miles away. Surrounding the core is the radiative zone, a dense region where energy moves outward through radiation. This part acts like a thick crowd at a concert, where energy has to slowly bounce from one atom to the next, absorbed and re-emitted countless times. It's an incredibly slow process. A single photon of light can take anywhere from thousands to millions of years to pass through this zone, zigzagging randomly like a drunk person trying to find their way out of a maze. The photons that warm your face today began their journey in the sun's core long before human civilization existed, perhaps even before our species evolved. After that comes the convective zone, where the mechanism of energy transport changes entirely. Here it's like a pot of boiling soup, with hot plasma rising toward the surface, cooling down, then sinking back down again in vast circular currents. These convection currents carry heat efficiently toward the surface, creating the granular pattern we see when we observe the sun through special telescopes. Each granule is about the size of Texas, a churning cell of superheated gas rising and falling in a continuous cycle. The sun's visible surface is called the photosphere, the layer from which the light we see is actually emitted. It's around 5,500 degrees Celsius, cooler than the interior but still hot enough to vaporize any known material instantly. That's what we see when we look at the sun through protective filters. A bright disk with occasional dark sunspots, regions where magnetic fields have temporarily cooled the surface. These sunspots can be larger than Earth itself, vast magnetic storms that come and go over days or weeks. Above the photosphere is the chromosphere, a reddish layer visible during solar eclipses, and then the corona, the sun's outer atmosphere. The corona is a mystery that has puzzled scientists for decades because it's far hotter than the surface beneath it. While the photosphere sits at thousands of degrees, the corona reaches into the millions of degrees Celsius. This seems to violate the basic rules of heat flow, which normally moves from hot to cold. The exact mechanism heating the corona is still being studied, though magnetic fields are almost certainly involved, somehow channeling energy from the sun's interior outward into this tenuous atmosphere. What we call sunlight is actually only a tiny part of what the sun sends out into space. It gives off ultraviolet rays that can burn our skin and damage our DNA. It radiates infrared heat that we feel as warmth on our faces. It produces radio waves that we can detect with specialized antennas, and X-rays that would be lethal in large doses. The sun also continuously sends out the solar wind, a stream of charged particles, mostly electrons and protons, that flows outward at speeds of several hundred kilometers per second. When these particles hit Earth's magnetic field, they can cause the beautiful displays we call auroras, the northern and southern lights that dance across polar skies. Sometimes the sun erupts more violently with solar flares or coronal mass ejections, shooting huge clouds of magnetized plasma into space at speeds approaching 1,000 kilometers per second. These eruptions can be billions of times more powerful than nuclear bombs. They can disrupt satellites, interfere with radio communications, and even induce currents in power grids on Earth strong enough to cause blackouts. In 1859, a massive solar storm called the Carrington Event caused auroras visible as far south as the Caribbean and disrupted the primitive telegraph systems of the time. If a similar event happened today, it could cause trillions of dollars in damage to our technology-dependent civilization. So the sun isn't always calm and steady. It has moods, cycles, active periods and quiet periods. It's alive with energy, constantly changing, constantly surprising us with new phenomena. The sun follows an 11-year cycle of activity, with solar maximum periods when sunspots and flares are common, and solar minimum periods when the surface is relatively calm. But even during quiet times, the sun is never truly inactive. The fusion continues, the energy flows outward, and the light that gives us life keeps streaming into space. The sun is made mostly of hydrogen, about 74% by mass, and helium, about 24%. The last 2% includes everything else: oxygen, carbon, nitrogen, iron, silicon, and traces of nearly every element in the periodic table. That may not sound like much, but that small fraction is tremendously important. It's what helped form the planets when the solar system was young, condensing out of the disk of gas and dust that surrounded the newborn sun. It's also one of the reasons we know the sun isn't a first-generation star, what astronomers call a population 3 star. It came from a cloud of gas and dust that had already been enriched by other stars that lived and died before it. Stars that forged heavy elements in their cores and scattered them into space when they exploded. In a way, the sun carries stardust in its DNA, the remnants of previous stellar generations mixed into its composition. In the classification system astronomers use to categorize stars, the Sun is called a G-type main sequence star, also known as a yellow dwarf. The term main sequence refers to the longest and most stable phase of a star's life, when it's fusing hydrogen into helium in its core. It's the kind of star that's not too big, not too small, sitting somewhere in the comfortable middle of the stellar spectrum. It's not the brightest or the hottest, but it's stable and long-lived. That's important because stars that are too massive burn out quickly, exhausting their fuel in just millions of years before exploding as supernova. The Sun, by contrast, is steady and reliable, burning its fuel at a measured pace. It's already been shining for about 4.6 billion years, and it's expected to last about 5 billion more before it begins to die, swelling into a red giant that will likely engulf the inner planets. But that end is so far in the future that it's almost meaningless on human timescales. For now, and for countless generations to come, the Sun will continue to shine steadily, providing the energy that makes life on Earth possible. And the Sun is big, truly enormous by earthly standards. The Sun makes up more than 99.8% of all the mass in our entire solar system. Every planet, moon, asteroid, comet, and grain of dust combined accounts for less than 0.2% of the total mass. If the whole solar system were a giant scale, the Sun would tip it almost completely, overwhelming everything else. Its gravity holds everything in orbit, from Mercury racing around close to the heat, to distant comets in the Oort cloud trillions of kilometers away. Without the Sun's gravitational pull, the planets would fly off into interstellar space, the architecture of our solar system would collapse, and Earth would become a frozen wasteland drifting through the darkness. So far, only a handful of spacecraft have been sent to study the Sun directly. Brave robotic explorers designed to withstand temperatures and radiation that would instantly destroy any human-made object not specifically protected. But none have been as ambitious as NASA Parker Solar Probe, launched in 2018. This remarkable spacecraft isn't flying straight into the Sun, which would be impossible with current technology. Instead, it's orbiting the Sun in an increasingly tight spiral, using gravity assists from Venus to shed orbital energy and dive closer with each pass. With help from Venus's gravity, each orbit brings Parker closer to the Sun, allowing it to enter the Sun's outer atmosphere, the corona, multiple times. At its closest approach, the probe passes within just a few million kilometers of the Sun's surface, closer than any spacecraft has ever ventured. At that distance, the spacecraft experiences temperatures exceeding 1,000 degrees Celsius and must hide behind a special heat shield made of carbon composite materials to survive. What makes this mission so important is what the probe is doing during those close passes. It's measuring the magnetic fields that ripple through the Sun's upper layers, trying to understand how energy flows from the surface into the corona. It's collecting particles from the solar wind, analyzing their composition and speed as they stream past at hundreds of kilometers per second. It's also recording bursts of solar energy during flares and storms, helping scientists understand how space weather forms and spreads, how these massive eruptions can affect planets across the solar system. Other missions have also watched the Sun, though from farther out and with different objectives. NASA SOHO, the Solar and Heliospheric Observatory, has observed solar storms and monitored the Sun's activity continuously since 1995, providing an unprecedented long-term record of solar behavior. The Solar Dynamics Observatory gives us stunning high-resolution images of solar activity in multiple wavelengths, capturing eruptions and flares in exquisite detail. Meanwhile, the European Space Agency's Solar Orbiter, launched in 2020, studies the Sun's poles and its magnetic fields from angles never seen before, regions that are impossible to observe from Earth's orbital plane. Together, these missions have transformed our understanding of our home star, turning it from a blinding ball of fire we couldn't look at directly into a rich subject of detailed scientific study. We've measured its heartbeat through the vibrations that ripple through its interior, a field called heliosysmology. We've tracked its mood swings as it cycles between active and quiet periods. We've mapped its winds, both the steady solar wind and the violent gusts that occasionally blast outward. And yet, despite all we've learned, mysteries remain. The corona heating problem is still unsolved. The exact mechanisms that trigger solar flares aren't fully understood. The sun continues to surprise us, teaching us new lessons about stellar physics with each observation. And yet, remarkable as it is, the sun is just one of many stars. It's special to us because we orbit it, because our very existence depends on its light and warmth. But in the grand scheme of the cosmos, it's only one average yellow star in a galaxy full of possibilities, one light among hundreds of billions. It's neither particularly large nor particularly small, neither especially hot nor especially cool. It's a middle-aged star in the middle of its life, unremarkable except for the fact that it's ours. Now, it's time to leave our home star behind. We lift our eyes from the sun and look outward, past the familiar planets, past Mars and Jupiter and the ice giants, past the frozen edge of our solar system, where the sun's gravitational influence begins to fade, toward the vast darkness between stars where the nearest neighbor waits in the cosmic night. Proxima Centauri awaits, a tiny red ember in the darkness, invisible to the naked eye but closer to us than any other star. It's not a bright beacon in the sky that you can spot on a clear night. You can't see it with your eyes, even on the clearest night far from city lights. Proxima Centauri is a red dwarf star, small and faint, barely glowing compared to the brilliant stars that dominate our night sky. If the sun were a blazing spotlight illuminating a stadium, Proxima would be more like a dim ember glowing in the corner of a dark room, easy to miss if you weren't looking for it. And yet, despite its faintness, despite its invisibility to human eyes, it's the closest star to us, our nearest stellar neighbor in the vast ocean of space. Our first stop in the sea of stars beyond our solar system. Proxima Centauri sits about 4.24 light-years away from the sun. That may sound close, and in cosmic terms it truly is. Stars in our galaxy are typically separated by several light-years, and many are hundreds or thousands of light-years distant. But 1 light-year is about 9.46 trillion kilometers, a distance so vast that it's hard to comprehend. Multiply that by 4.24, and you get a distance of over 40 trillion kilometers, a gulf of emptiness that separates us from even our nearest neighbor. That's so far that no spacecraft we've ever built has come even remotely close to crossing it. Even if you were riding on Voyager 1, the fastest object humans have ever sent into deep space, traveling at about 17 kilometers per second relative to the sun, it would still take more than 73,000 years to reach Proxima Centauri. That's longer than all of recorded human history. Imagine driving your car non-stop at highway speed. You wouldn't reach Proxima Centauri in your lifetime, or your children's lifetimes, or their children's lifetimes. You'd need thousands of generations, an unbroken chain of travelers spanning the entire history of human civilization from the first farmers to the present day, just to make the trip. That's how far even our nearest neighbor is, how vast the gulfs between stars truly are. Proxima is about 1/8 the mass of the Sun, just 12% as heavy. Despite being a star, despite being a ball of fusion-powered plasma, it's remarkably small. Its diameter is around 200,000 kilometers, or roughly 1.4 times the size of Jupiter. That's tiny for a star, smaller than many of the gas giant planets we've discovered orbiting other stars. If you replaced our Sun with Proxima Centauri, Earth would freeze over almost immediately. Its light wouldn't be nearly enough to keep our planet warm, and the temperature would plummet to hundreds of degrees below zero within weeks as the oceans froze and the atmosphere began to condense. In fact, if you stood on Earth and looked up at a sky with Proxima as our star, replacing the brilliant sun we know, the sky would look almost pitch black even at noon. The star would appear as a dull, reddish point, barely brighter than a full moon, casting a dim crimson glow over the frozen landscape. It's that faint, that weak compared to our sun. The stars would be visible all day long, twinkling in a permanently dark sky even at the star's zenith. Proxima's surface temperature is also much lower than the sun's. While the sun's photosphere sits at around 5,500 degrees Celsius, Proxima is only about 3,000 degrees. That cooler temperature gives it its characteristic reddish glow, the signature of red dwarf stars. The color comes from the wavelengths of light it emits most strongly, with its peak output shifted toward the red and infrared parts of the spectrum. It gives off only about 0.17% of the sun's total energy output, less than 1/5 of 1%. So it's quiet, soft, dim, and in many ways invisible to anyone looking at the night sky without optical aid. But don't let the small size fool you. Don't let the dim light make you think this is a boring or inactive star. Proxima is still a living star, still fusing hydrogen into helium in its core, still generating energy through nuclear reactions. And it has a personality, one that's not always calm or gentle. Proxima is known for being active in ways that can be violent and unpredictable. It's what astronomers call a flare star, a type of variable star that randomly blasts out huge flares of radiation and charged particles from its surface. These stellar flares come from magnetic storms that snap and crack in Proxima's atmosphere, suddenly releasing enormous amounts of stored magnetic energy in bursts that can last from minutes to hours. Sometimes these flares are many times stronger than anything the sun puts out, increasing the star's brightness by significant amounts for brief periods. For any planet orbiting close to such a star, these flares pose a significant threat to habitability. They can strip away atmospheres over time, the intense radiation and particle winds gradually eroding the protective blanket of gas that keeps a planet's surface hospitable. They can damage surfaces with intense bursts of ultraviolet and X-ray radiation, destroying complex organic molecules. And they make the environment unstable for life as we know it, subjecting any potential organisms to sudden bursts of lethal radiation. And yes, Proxima does have planets orbiting it, worlds that circle this dim red star in the darkness. In 2016, a team of astronomers led by Guillaume Anglada Escudé made a breakthrough discovery that captured headlines around the world. They found a planet orbiting Proxima Centauri, a world that would become known as Proxima b, potentially the closest exoplanet to Earth. The discovery of this world came from years of patient, careful observation and painstaking data analysis. The team was part of the Pale Red Dot campaign, an international effort specifically designed to look for planets around our nearest stellar neighbor. They used a method called the radial velocity technique, also known as the Doppler method, which is one of the most successful ways to find planets around other stars. This method doesn't detect the planet directly by imaging it or seeing it pass in front of its star. Instead, it looks at how the star moves in response to the planet's gravity. As a planet orbits a star, its gravity tugs on that star just a tiny bit, causing the star to wobble back and forth in space. Both the star and planet actually orbit their common center of mass, though for a star and planet that center of mass is usually inside or very close to the star. These wobbles are incredibly small, often just a few meters per second, but they can be measured using sensitive instruments that detect tiny shifts in the star's spectrum. In this case, they used the HARP spectrograph, mounted on the 3.6-meter telescope at the European Southern Observatory in La Silla, Chile. HARP stands for High Accuracy Radial Velocity Planet Searcher, and it's like a stethoscope for stars, listening for the subtle movements that betray the presence of orbiting planets. It works by splitting starlight into its component colors and looking for tiny shifts in the positions of absorption lines, dark lines that appear at specific wavelengths. When a star moves toward us, even slightly, these lines shift toward the blue end of the spectrum. When it moves away, they shift toward the red. By measuring these shifts with extreme precision, astronomers can detect the back-and-forth wobble caused by an orbiting planet. Over many months of observation, they noticed a regular, repeating pattern in Proxima Centauri's motion. The star was wobbling with a period of 11.2 days, moving toward us and then away from us in a rhythmic cycle. That wobble meant something was pulling on it gravitationally, something with significant mass orbiting the star. Based on the size of the wobble and the known mass of the star, they calculated that the planet doing the tugging was at least 1.17 times the mass of Earth, making it roughly Earth-sized or perhaps slightly larger. The planet orbits its star once every 11.2 days, meaning its year is less than 2 weeks long. That's because it's extremely close to Proxima, orbiting at a distance of only about 7.5 million kilometers. For comparison, Mercury, the closest planet to our Sun, orbits at about 58 million kilometers. Proxima b is practically hugging its star, closer to Proxima than Mercury is to the Sun. But here's the interesting part. Because Proxima is so dim and cool, this close distance actually puts the planet in what scientists call the habitable zone, sometimes called the Goldilocks zone. This is the region around a star where temperatures are just right for liquid water to exist on a planet's surface, not too hot that it all evaporates, not too cold that it all freezes. For a dim star like Proxima, the habitable zone is much closer than it is for our Sun. But being in the habitable zone doesn't mean the planet is actually habitable. Could have liquid water doesn't mean does have liquid water. The problem is that Proxima's flares might be strong enough to destroy or severely damage any atmosphere the planet might have had. Without an atmosphere, water can't stick around in liquid form. No air means no atmospheric pressure to keep water liquid rather than boiling away into space. No atmosphere means no protection from the intense radiation during flares. And no atmosphere means no climate stability, no weather, no protection from meteorite impacts. Some scientists still think it's possible that Proxima b might have some form of magnetic shield, similar to Earth's magnetic field, but perhaps even stronger. A powerful magnetic field could deflect some of the charged particles from stellar flares, creating a protective bubble around the planet. But so far, we just don't know. We haven't seen the planet's surface directly. We have no photographs, no landers, no direct observations of its atmosphere or magnetic field, just these distant, indirect measurements of its mass and orbit. Later observations suggested another planet in the system, designated Proxima c. This one orbits much farther out from the star and appears to be much larger, possibly a mini-Neptune, a planet several times the mass of Earth with a thick atmosphere of hydrogen and helium. It's not likely to be habitable given its size and composition, but it's interesting because it suggests Proxima has a multi-planet system, not just a single world but a family of planets at different distances. And there might be even more planets waiting to be discovered. A third potential planet, Proxima d, has been hinted at in more recent data. It appears to be very small, possibly less than a quarter the mass of Earth, and orbits very close to the star, even closer than Proxima b. Whether it's a real planet or just a statistical artifact, noise in the data that creates the appearance of a signal is still being debated among astronomers. Confirmation will require more observations, more data, more years of patient monitoring. Despite being the closest star system to Earth, despite being our nearest neighbor among all the stars, no spacecraft has ever come close to reaching Proxima Centauri. Our farthest traveled probe, Voyager 1, was launched way back in 1977, and after nearly 50 years of continuous travel through space, it's still inside our cosmic backyard, less than a seventh of a light year away. At its current pace of about 17 kilometers per second, it would take more than 73,000 years to reach Proxima, and that's assuming it was even aimed in the right direction, which it isn't. The gap between our current capabilities and what would be needed for interstellar travel isn't just a matter of distance. It's a matter of technology, of physics, of engineering challenges we haven't yet solved. Our fastest spacecraft barely reach a tiny fraction of 1% of the speed of light. To reach even the nearest stars within a human lifetime would require speeds thousands of times faster than anything we've ever achieved. But that hasn't stopped people from dreaming, from imagining, from proposing bold concepts that push at the boundaries of what might be possible. One of the most ambitious concepts yet proposed for interstellar travel is called Breakthrough Starshot, a project announced in 2016 by Russian billionaire and technology investor Yuri Milner, with support and endorsement from renowned physicist Stephen Hawking and Facebook founder Mark Zuckerberg. The goal is remarkably ambitious: to send a fleet of tiny interstellar probes called star chips to Proxima Centauri within a human lifetime, to make the journey in decades rather than millennia. Each probe in this fleet would be extraordinarily small, no larger than a coin, weighing only a few grams. They wouldn't carry conventional rockets or chemical propulsion systems. Instead, each tiny spacecraft would be attached to an ultra-thin, lightweight sail about 4 meters wide, made of advanced materials like graphene or specially designed reflective polymers, just a few atoms thick. The plan is both simple and extraordinary. Fire an array of powerful Earth-based lasers at these sails, pushing them using nothing but light pressure. Light has momentum, and when photons from a laser bounce off a reflective surface, they transfer that momentum, creating a tiny push. With enough laser power focused on these sails, with a beam of light intense enough, the probes could be accelerated to incredible speeds, potentially reaching up to 20% the speed of light, about 60,000 kilometers per second. At that speed, these tiny spacecraft could reach Proxima Centauri in just over 20 years, a journey that could begin and end within a single human lifetime. It would be our first chance to send something to another star system and get results back while the people who launched it are still alive. These tiny spacecraft would carry miniaturized cameras, sensors to measure magnetic fields and radiation, and communication tools to send data back to Earth, all shrunk down to fit in a package no bigger than a microchip. The engineering challenges are immense. The sails would need to be incredibly reflective, but also incredibly strong to survive the initial acceleration without tearing. The laser array would need to be enormous, perhaps kilometers across, and powerful beyond anything currently built. The navigation would need to be perfect, since there would be no way to steer once the probe was launched. And the communication system would need to send signals across light years of space, requiring years for the message to reach Earth, even traveling at the speed of light. Once there, if everything worked perfectly, these tiny probes could snap images of Proxima's planetary system, photograph Proxima b from close range, study its atmosphere if it has one, measure its magnetic field, and send all that data back to Earth. The signal would take another 4.2 years to reach us, meaning we'd see the results about 24 years after launch. It would be our first direct look at a planet in another star system, our first close-up view of an alien world. And for that first historic visit, Proxima makes a natural target. not just because it's the closest star, but because it's part of something bigger, part of a multiple star system that includes other nearby stars. And that's where we're heading next, deeper into the Alpha Centauri system. As we drift farther from Proxima Centauri's dim red glow, the darkness of space seems to thicken again, wrapping around us like a heavy blanket. But we don't go far. Just over 0.2 light-years away, still within the same cosmic neighborhood, still part of the same gravitationally bound system, two brighter stars come into view. They shine with a steady, familiar warmth, not too different from our own sun, stars that could almost be siblings to the one we left behind. These are Alpha Centauri and Alpha Centauri b, the second closest star system to Earth, and the next destination on our journey through the local neighborhood. Together with dim Proxima orbiting distantly around them, these two stars form a triple star system known collectively as Alpha Centauri. While Proxima is the closest individual star to Earth, Alpha Centauri and b are the most visible members of this stellar family, the ones you can actually see from Earth without a telescope. In fact, if you live in the southern hemisphere and look up on a clear night, you've almost certainly seen them already, though you might not have known what you were looking at. To the naked eye, they appear as a single bright point of light, one of the brightest stars in the night sky, shining steadily in the constellation Centaurus. What you're actually seeing, though you can't tell without optical aid, are two stars so close together in our sky that your eyes can't separate them. They blend into one brilliant point. But through even a modest telescope, they separate into two distinct stars, two golden lights dancing around each other in slow, precise loops, bound together by gravity in an eternal waltz through space. It's a beautiful sight, one that has captivated astronomers for centuries. Astronomers have known about Alpha Centauri for a very long time. It was first properly catalogued in 1603 by German astronomer Johann Bayer, who created one of the first comprehensive star atlases. He gave it the name Alpha Centauri because it was the brightest star, the Alpha star, in the constellation Centaurus, following the naming convention he established that is still used today. For a long time, for centuries, people believed it was just one star, a single point of light shining steadily in the southern sky, unremarkable except for its brightness. It was only when telescopes became powerful enough in the late 18th and early 19th centuries that scientists realized there was more to the story, that this single point of light hid a secret. What looked like one star to the naked eye turned out to be two separate stars when viewed through a telescope. Two bright stars orbiting each other in a slow, graceful loop, companions bound together by mutual gravitational attraction. These were eventually designated Alpha Centauri and Alpha Centauri b, the two main components of the system. Then came another surprise, a discovery that wouldn't happen for more than another century. In the early 20th century, astronomer Robert Innes, working at the Union Observatory in Johannesburg, South Africa, discovered a third star nearby. It was Proxima Centauri, that faint red dwarf we just visited, hiding in plain sight all along. It was dim, incredibly dim and distant from the main pair, separated by about 0.2 light-years. But careful measurements showed it was moving in the same direction through space as Alpha Centauri and b, traveling with them through the galaxy. Over time, through decades of careful observation and orbital calculations, scientists confirmed that Proxima was gravitationally bound to Alpha Centauri and b, part of the same system, despite its distance. The three stars form a triple star system, a cosmic family orbiting their common center of mass over the course of millions of years. Proxima takes perhaps 500,000 years or more to complete one orbit around the central pair, a stately dance measured on timescales that dwarf all of human existence. So what we once thought was a single light in the night sky, just another star among thousands visible to ancient observers, turned out to be 3 stars, a close-knit family quietly orbiting together across unimaginable spans of time. It's a reminder of how much is hidden from our unaided eyes, how the universe holds secrets that only reveal themselves when we look more carefully. Later in the 19th century, scientists like Thomas Henderson and Manuel John Johnson took the next crucial step in understanding this nearby system. They used a method called stellar parallax to measure how far away Alpha Centauri really was, to put a number on the distance that separated us from our nearest stellar neighbors. The parallax method is beautifully simple in concept, though challenging in practice. As Earth moves around the Sun over the course of a year, our viewpoint shifts. We see the solar system from slightly different angles as we orbit. Nearby stars appear to shift slightly in position against the backdrop of more distant stars, which are so far away they don't seem to move at all. It's the same effect you see when you close one eye and then the other. Nearby objects seem to jump position against the distant background. By measuring that tiny shift in a star's position and knowing the size of Earth's orbit around the Sun, astronomers can use simple geometry to calculate the star's distance. It's triangulation on a cosmic scale, using the diameter of Earth's orbit as the baseline of a triangle that stretches across light years. Their results, refined over many years of observation, revealed something astonishing. This bright star system wasn't just another distant point of light. It was our nearest stellar neighbor, sitting just 4.37 light-years away, closer to us than any other star except Proxima itself. The discovery helped establish the scale of interstellar space, giving us our first real understanding of how far apart stars actually are. With the system mapped and its distance measured, let's slow down now and meet the stars themselves, one by one, examining their properties and characteristics in detail. Alpha Centauri is the larger and brighter of the 2 main stars. It's about 10% more massive than our Sun, not dramatically different but noticeably bigger. Its luminosity is roughly 1.5 times that of the Sun, meaning it pours out more energy into space. Its surface temperature is around 5,800 degrees Celsius, just a bit hotter than the Sun's 5,500 degrees. If you could somehow replace our Sun with Alpha Centauri A, Earth would still be in the habitable zone, still receiving enough energy to maintain liquid water on its surface. Life might continue much as it is now, though the increased light and warmth would create a slightly different climate. The seasons might be a bit warmer. The polar ice caps might shrink. But overall, it would be similar enough that Earth could remain habitable. This star is classified as a G2V type star, using the spectral classification system astronomers employ. The G2 designation means it's a yellow dwarf star, just like the Sun. In fact, Alpha Centauri is often described as nearly identical to our Sun, like a cosmic twin or at least a very close sibling. The V designation indicates it's a main sequence star, actively fusing hydrogen into helium in its core, in the prime of its stellar life. A star like this can live for billions of years, roughly 10 billion years total from birth to death. Alpha Centauri is thought to be between 4 and 6 billion years old, similar in age to our Sun, meaning it's roughly middle-aged. It has billions of years ahead of it before it begins to run out of hydrogen fuel and starts its evolution into a red giant. Alpha Centauri B is the smaller and fainter companion, but only by comparison. It's still a very respectable star by cosmic standards. It's about 90% the mass of the Sun, just slightly smaller, and shines with about half the Sun's brightness. Its surface temperature is around 5,300 degrees Celsius, a bit cooler than both the Sun and Alpha Centauri A, which gives it a slightly more orange color compared to Alpha Centauri A's yellow-white glow. This star is classified as a K1V type star. The K designation places it in the orange dwarf category, stars that are cooler and smaller than yellow dwarfs like the Sun. These types of stars tend to be quieter, less active, and live even longer than stars like our Sun. An orange dwarf can burn steadily for 15 or even 20 billion years, far longer than the universe has currently existed. The two stars, A and B, orbit each other in a bound binary system, locked in a gravitational dance that will continue for billions of years. They complete one full orbit around their common center of mass every 79.91 years. That means one complete loop takes nearly 8 decades, longer than a typical human lifetime. If you watch them through a telescope at the start of your life, you might see them complete one full orbit before you died. Their orbit isn't a perfect circle. It's more of an oval, what scientists call an ellipse, with the stars sometimes closer together and sometimes farther apart. At their closest approach, called periastron, they're about 11 astronomical units apart, 11 times farther than Earth is from the Sun. That's roughly the distance from the Sun to Saturn. At their farthest separation, called a pastron, that distance stretches out to 35 astronomical units, similar to the distance from the Sun to Neptune. Even at their closest, the stars are far enough apart that they don't seriously interfere with each other's potential planetary systems. Their gravitational influence on each other is significant, enough to keep them bound together, but they're not so close that they strip planets away from each other or destabilize planetary orbits. This gives each star its own space to potentially host a family of planets, its own habitable zone where rocky worlds might orbit at just the right distance for liquid water. And that's where things get really interesting, where the story shifts from academic astronomy to the tantalizing possibility of finding Earth-like worlds orbiting Sun-like stars. For decades, astronomers have searched for planets around Alpha Centauri A and B. It seemed almost inevitable that such Sun-like stars would have planetary systems. After all, planet formation appears to be a natural byproduct of star formation. When a star forms from a collapsing cloud of gas and dust, the leftover material settles into a disk around the young star, and planets gradually condense out of that disk. Why wouldn't Alpha Centauri have planets? For a long time, though, the searchers found nothing certain, nothing definitive. It was frustrating for the astronomers involved. Here we have stars so close, so accessible, so similar to our Sun, and yet no planets we could confirm with confidence. The problem was partly technical. The stars are bright and close together in the sky, making it hard to detect the subtle signals of planets. And any planets that exist might be small, Earth-sized or smaller, creating signals too faint to detect with the instruments available. But in 2012, scientists from the European Southern Observatory announced they had detected a planet orbiting Alpha Centauri b. They called it Alpha Centauri bb, following the naming convention where the star gets a capital letter and its planets get lowercase letters. It was believed to be a rocky world, perhaps roughly Earth-sized, orbiting its star every 3.2 days. The orbit was extremely close, much closer than Mercury to the Sun, which meant the planet would be scorched by its star's heat, far too hot for life as we know it. Surface temperatures would be over 1,000 degrees Celsius, hot enough to melt lead. But it was still exciting because it suggested that planets could form and survive in this binary star system, that the presence of two stars didn't prevent planet formation. Unfortunately, as more data came in and other teams analyzed the observations, doubts began to emerge. The signal was weak and appeared only in certain datasets. Later reviews suggested it might have been a false positive, an artifact caused by noise in the data or possibly by the star's own activity creating signals that mimicked a planet. For now, Alpha Centauri bb remains unconfirmed, neither definitely real nor definitely ruled out, stuck in astronomical limbo. Years later, in 2021, astronomers using a telescope called the Very Large Telescope in Chile's Atacama Desert discovered something else. Another possible planet, but this time around Alpha Centauri A. The planet wasn't detected through the radial velocity method that found Proxima b. Instead, it was hinted at through a different technique called direct imaging, which looks for the faint light or infrared warmth of a planet rather than measuring the star's wobble. This potential object was detected at a distance from Alpha Centauri, a roughly similar to where Neptune orbits our Sun, far out in the system's outer reaches. If confirmed through additional observations, it would be a giant planet, maybe something like Saturn or Jupiter, orbiting quietly on the edge of its system, a cold world of gas and ice far from its star's warmth. The detection is still tentative, still awaiting confirmation through additional observations with different instruments. Direct imaging is difficult because planets are so much fainter than their parent stars. It's like trying to see a firefly next to a searchlight. But the technology is improving every year, and we may soon know for certain whether this planet is real. More discoveries might still lie ahead, waiting for better instruments and more sensitive detection methods. The Alpha Centauri system is now a top priority target for exoplanet hunters, especially those looking for Earth-like worlds in the habitable zones of Sun-like stars. NASA upcoming missions and telescopes, including the James Webb Space Telescope, which is already operational and returning stunning data, along with future planned observatories, may help us finally get a clearer look at any planets that orbit these nearby stars. The system has also inspired dreams of interstellar missions, of actually sending spacecraft to visit these nearby stars. Before breakthrough, Starshot focused its attention on Proxima Centauri. Alpha Centauri and B were often mentioned as the primary destinations, the obvious first targets for humanity's first journey to another star system. You've probably heard the name Alpha Centauri before, even if you've never looked at the night sky. It appears frequently in science fiction films, novels, video games, and television shows. It's a favorite setting for stories about alien civilizations, future space colonies, or interstellar missions gone wrong. It appears in Avatar, where the lush moon Pandora orbits a planet in the Alpha Centauri system. It's referenced in Mass Effect, Sid Meier's Alpha Centauri, and dozens of other works of science fiction. That's no accident, no random choice by writers and creators. Alpha Centauri represents something powerful in the human imagination. It's the closest place beyond our solar system that feels like it could be something like home, the nearest stars that resemble our sun enough to make us wonder if there's anywhere in our cosmic neighborhood where life like ours could exist, where humans might one day establish a presence among the stars. Alpha Centauri feels like the most likely candidate. And if we ever did manage to stand on a planet in the Alpha Centauri system, if we ever sent astronauts or established colonies there in some distant future, the view of the sky would be unlike anything visible from Earth, strange and beautiful and alien. From a planet orbiting Alpha Centauri A, you'd see Alpha Centauri B shining brightly in the sky, far brighter than Venus appears from Earth, bright enough to cast distinct shadows and provide significant light even at night. It would move slowly across the sky over the course of decades as the two stars orbited each other, sometimes appearing as a morning star, sometimes as an evening star, sometimes hanging in the night sky all night long. If the system has moons, or if the planet has rings like Saturn, they'd be bathed in a complex interplay of light, illuminated by two suns from different angles, creating lighting conditions we can barely imagine. Proxima Centauri, though distant from the main pair, would still be part of the system, appearing as a faint red dot in the background, visible perhaps only through telescopes, still part of the family just much farther away. Alpha Centauri. And B, show us what it looks like when stars share a space and still manage to shine on their own, each one distinct yet bound to the other. Two suns circling slowly in the dark, whispering possibilities of worlds that might orbit them, of climates shaped by two stars instead of one, of skies with two sources of light. If there are planets there, especially in the right orbital zones, in the habitable regions where water could remain liquid, then it's not hard to wonder what kind of climates they might have. What would weather be like on a world heated by two stars? What kinds of skies might exist? What colors might dominate the landscape under the light of yellow and orange suns? And maybe, just maybe, what kind of life might have evolved there if conditions were right? For now, we can only listen and watch and imagine, pointing our telescopes at these nearby stars, analyzing the light that has traveled for years to reach us, looking for the subtle signs of planets. But our journey doesn't stop here in this triple star system. There's another star just a little farther out, just beyond Alpha Centauri in our expanding circle. It's not bright or flashy. It doesn't shine like Sirius or glow warmly like Alpha Centauri. In fact, it's one of the dimmest stars visible through telescopes, barely noticeable even when you know exactly where to look. But it's famous in astronomical circles, studied for over a century, and it has one remarkable characteristic that makes it stand out. It moves faster than any other star in the night sky, racing through space at tremendous speed. Our next destination is Barnard's Star, the silent sprinter of the stellar neighborhood. At first glance, as we approach through the darkness, there's not much to see. You can't spot it with your eyes from Earth, even on the clearest night in the darkest location far from any city lights. It doesn't glow warmly like Alpha Centauri A. It doesn't blaze like the stars that dominate our constellations. It's dim, quiet, almost invisible, a faint red ember against the black. But don't let that fool you. Don't let the dimness make you underestimate this star. This little red star is on the move, racing through the galaxy faster than any other star near us. And despite its small size and quiet nature, despite being almost invisible to anyone looking at the sky, Barnard's Star has captured the imagination of astronomers for more than a century, becoming one of the most studied stars beyond our solar system. Barnard's Star lies about 5.96 light-years away from Earth, which translates to around 56.4 trillion kilometers of empty space separating us from it. That's just a bit farther out than Alpha Centauri, placing it fourth on the list of nearest stars to the Sun when you count individual stars rather than systems. It's not far in cosmic terms, but far enough that visiting it would still require tens of thousands of years using today's spacecraft technology. The star is named after American astronomer Edward Emerson Barnard, who discovered its unusually fast movement across the sky in 1916. At the time, what shocked scientists wasn't the star's distance, which was already approximately known. It was the speed at which it appeared to be moving relative to the background stars. Barnard noticed that the star seemed to be shifting its position in the sky much more quickly than other stars, racing across the celestial sphere at a rate that was unprecedented. By measuring its position carefully over the course of years and comparing it to older photographic plates and observations, he realized it had what astronomers call a high proper motion, the fastest proper motion ever recorded at that time. Proper motion refers to a star's apparent movement across the sky as seen from Earth, the angular change in position over time. Most stars appear essentially fixed in position because they're so far away that even though they are moving through space, the change in angle is too small to notice over human timescales. But nearby stars, especially if they are moving quickly through space, can show noticeable proper motion over years or decades. Barnard's Star moves about 10.3 arcseconds per year across the sky. An arcsecond is a tiny angle, 1/3600th of a degree, so this might not sound like much. But in star terms, it's like watching a snail sprint across a sidewalk. It's extraordinarily fast for a star. Over a human lifetime of 70 or 80 years, Barnard's star noticeably changes its position relative to the background stars, moving by several arc minutes, enough that careful amateur astronomers can track its motion. Over a period of just 180 years, Barnard's star moves across the sky by a distance equal to the diameter of the full moon. That's incredibly fast for a star, fast enough that ancient astronomers, had they kept detailed enough records, would have noticed its motion over centuries. Now, let's zoom in closer to this fast traveler and examine it in detail. Barnard's star is a red dwarf, a type of star much smaller and cooler than our Sun. Specifically, it's classified as a spectral type M4 star, placing it well into the red dwarf category. That means it's deep in the red part of the stellar spectrum, with a surface temperature of only about 3,100 degrees Celsius. Our Sun, for comparison, has a surface temperature of around 5,500 degrees. Barnard's star is nearly half as cool, and that difference in temperature has dramatic effects on its brightness and color. Because it's so cool by stellar standards, Barnard's star doesn't shine very brightly at all. Its total luminosity, the amount of energy it pours out into space, is just 0.04% that of the Sun, less than 1/25th of 1%. If the Sun were a blazing spotlight visible from miles away, Barnard's star would be a dim red nightlight tucked away in a corner, easily overlooked. You'd need a good telescope to see it at all, and even through a telescope it appears as just a faint reddish point, unremarkable except for its motion. Despite being dim and small, Barnard's star is old, really old by stellar standards. Current estimates suggest it's between 7 and 12 billion years old, somewhere in that vast range. That's almost twice the age of our Sun, which is about 4.6 billion years old. Think about that for a moment. This small, quiet star has been burning steadily for most of the life of our galaxy, perhaps even since before our solar system existed. It's already lived through generations and generations of more massive stars being born, living their brief bright lives, and dying, some of them exploding as supernova and enriching the interstellar medium with heavy elements. And Barnard's star just keeps going, burning slowly and steadily, with trillions of years still ahead of it. Red dwarfs like Barnard's star burn their fuel incredibly slowly compared to larger stars. Unlike massive stars that blaze through their hydrogen fuel and die young, living for only millions of years before exploding, red dwarfs are extraordinarily frugal with their fuel. They sip their hydrogen slowly, fusing it at a measured pace that allows them to shine for what seems like forever in human terms. A red dwarf like Barnard's star can live for several trillion years, far longer than the current age of the universe, which is only about 14 billion years. The universe isn't old enough yet for any red dwarf to have died of old age. They're all still in their youth or middle age, even the oldest ones, still happily fusing hydrogen in their cores. In terms of size, Barnard's star is tiny even for a red dwarf. It's only about 14% the mass of our Sun, about 1/7 as heavy. Its diameter is roughly 20% of the Sun's diameter. If you could line them up side by side, the Sun would tower over Barnard's star like a beach ball next to a marble, dwarfing it completely. It's small, but it's stable and relatively peaceful. It hasn't shown much of the wild, violent flaring that some red dwarfs are known for, the kind of stellar temper tantrums that Proxima Centauri regularly displays. That makes Barnard's star a more peaceful, more stable environment, which is what scientists love to see when thinking about possible planets or even future exploration. And yes, Barnard's star has kept astronomers busy for decades with the question that drives so much of modern astronomy. Does it have planets orbiting it? For decades, scientists searched, using increasingly sophisticated techniques and instruments. In the 1960s, Dutch-American astronomer Peter van de Camp claimed he had found evidence of a planet, maybe even two planets, orbiting Barnard's star based on careful measurements of tiny changes in the star's position. He spent years analyzing photographic plates taken through the 61-centimeter refractor telescope at Sproul Observatory, measuring tiny wobbles in the star's motion that he attributed to the gravitational tug of orbiting planets. His announcement generated tremendous excitement. The idea of finding a planet around our second nearest stellar neighbor, a planet that might be detectable and eventually photographed, captured the imagination of scientists and the public alike. But science requires verification, and when other astronomers attempted to confirm Van de Camp's findings using different telescopes and methods, they couldn't reproduce his results. Later reviews showed that the wobbles he saw were likely caused by systematic errors in his telescope, perhaps changes in the instrument itself or problems with how the photographic plates were handled. It was a major disappointment at the time, a cautionary tale about the difficulty of planetary detection and the importance of independent verification. For years afterward, Barnard's star was thought to be lonely, a solitary star with no planetary companions. But the search never truly stopped. As technology improved, as spectrographs became more sensitive, as data analysis techniques became more sophisticated, astronomers returned to Barnard's star again and again. And in 2018, nearly a century after Barnard first measured the star's rapid motion, a team of astronomers made a breakthrough using precise radial velocity data accumulated over many years of patient observation. They detected signs of what appeared to be a planet, a world orbiting this ancient red dwarf. The discovery came from combining data from two powerful spectrographs, Carmines, based in Spain, and HARPS, which we've already encountered in Chile. Both instruments are among the best in the world at detecting the tiny wobbles in a star's motion caused by orbiting planets. They work by measuring tiny shifts in the star's spectral lines with extraordinary precision, detecting velocity changes of just a meter or two per second. What they found was compelling enough to announce. A planet roughly 3.2 times the mass of Earth, what astronomers call a super-Earth, orbiting Barnard's star every 233 days. It was named Barnard's star B, following the standard naming convention. That orbital period, nearly 8 months, puts the planet at a distance of about 60 million kilometers from its star, somewhere between the distances of Mercury and Venus from our Sun. If it were in our solar system at that distance, it would be comfortably warm. But remember, Barnard's star is much dimmer than our Sun. Now, before we get too excited about the possibility of another habitable world, we need to consider the reality of the situation. While the planet orbits at what seems like a reasonable distance, it likely lies just outside the so-called habitable zone for Barnard's star. Because the star is so dim, the habitable zone is much closer than it is for our Sun, and at 60 million kilometers, the planet is probably too far out to receive enough warmth. Estimates suggest surface temperatures on Barnard's star B hover around -70 degrees Celsius, colder than Antarctica in winter, colder than the coldest temperatures ever recorded on Earth. That's comparable to the surface of Mars, or even colder. Any water on the surface would be frozen solid, locked in ice that might never melt. Still, the discovery was and remains tremendously significant. It's one of the nearest known exoplanets to Earth, one of the closest worlds beyond our solar system. And even if it's frozen on the surface, some scientists wonder whether there could be other possibilities. Could there be subsurface oceans kept liquid by radioactive decay in the planet's interior, similar to what we suspect exists on Jupiter's moon Europa? Could there be geothermal activity, volcanic vents that create pockets of warmth? Could life, if it exists, have found ways to survive in protected niches? We don't know yet, and we won't know for certain until we can study the planet more directly. But Barnard's star B is now one of the top candidates for future telescope observations, for atmospheric studies if it has an atmosphere, and even for theoretical future missions. As for sending spacecraft there, we're nowhere close to having the capability. No mission has ever been launched with Barnard's star as its destination. At our current technology level, with our fastest spacecraft traveling at less than a tiny fraction of 1% of light speed, it would still take tens of thousands of years to reach this system. But that doesn't stop us from planning, from imagining, from designing missions that might one day be possible. Projects like Breakthrough Starshot, which we discussed earlier, could theoretically be aimed at Barnard's star instead of, or in addition to Proxima Centauri. If we could build light-sail spacecraft that travel at a significant fraction of light speed, this quiet ancient star might one day receive a visitor from Earth, a tiny probe carrying a message from a younger civilization. Before we leave Barnard's star and continue our journey outward, there's one more fascinating detail worth mentioning, something that makes this star even more interesting from a long-term perspective. Because Barnard's star is moving so quickly through space, and because it's heading roughly in our direction, it's actually getting closer to us over time. Right now, it's the fourth nearest star to Earth. But in about 10,000 years, around the year 12,000 AD, it will reach its closest point to us, passing by at a distance of just 3.8 light years. At that point, it will be closer than Proxima Centauri is today, becoming temporarily the closest star to our solar system. It won't stay there, of course. Its tremendous velocity will carry it past us and then away again, gradually receding into the distance. But for a brief moment in cosmic terms, a span of perhaps 20,000 years or so, Barnard's star will be our nearest neighbor, closer than any other star except the Sun itself. It's a reminder that the stellar neighborhood isn't static. Stars move through the galaxy at different speeds and in different directions. The list of nearest stars changes over time. Stars that are close now will drift away. Stars that are distant now will eventually come near. The neighborhood is dynamic, alive with motion, though the changes happen so slowly that thousands of human generations pass between noticeable shifts. But for now, Barnard's star remains what it has been for centuries. A quiet, stable, ancient red dwarf, racing through space faster than any nearby star, carrying at least one frozen world in tow and possibly harboring secrets we haven't yet discovered. And with that, we drift onward through the darkness. The next light ahead is even harder to see than Barnard's star, even fainter, even more challenging for our telescopes to detect. It's one of the faintest stars in our cosmic neighborhood, a red dwarf like Barnard's but with almost no visible activity, no remarkable motion, nothing that makes it stand out except its extraordinary faintness. You wouldn't notice it unless you were specifically looking for it, searching that particular patch of sky with sensitive instruments. But it's there, quiet and stable and practically invisible, waiting in the darkness. Wolf 359 waits ahead, one of the faintest, most invisible stars in our local neighborhood. If you turned off every light, stepped outside on the clearest night imaginable, found a location far from any city with perfectly dark skies, and looked straight up at exactly the right spot, you wouldn't see it. You could stare for hours, let your eyes fully adjust to the darkness, scan every inch of that region of sky, and still you'd miss it completely. That's how dim our next destination is, how utterly invisible to human eyes. At just under 8 light-years away, about 7.9 light-years to be more precise. Wolf 359 is one of our nearest stellar neighbors. It's relatively close in cosmic terms, closer than dozens of other stars, well within what we consider our local neighborhood. Yet it's completely invisible to the unaided human eye, too faint to trigger our retinas even in perfect conditions. You could be looking right at it, staring directly at the point in space where it sits, and not know it was there. It's a ghost among stars, a cosmic whisper, so faint that only telescopes can reveal its presence. But it's real, it's there. And now here we are, approaching one of the faintest stars in our entire celestial backyard. The moment we arrive, the quiet is overwhelming. Wolf 359 doesn't roar with fusion like the sun. It doesn't erupt with flares like Proxima. It doesn't blaze with light like Sirius. It just sits there, humming in infrared silence, glowing dimly like a dying coal in a frozen cave, barely putting out enough light to notice. It's a red dwarf, yes, like Proxima and Barnard's, but even by red dwarf standards it's on the extreme end of the scale. It's one of the faintest red dwarfs known, pushing the lower limits of what can still be called a star rather than a brown dwarf. Its mass is just 9% that of the Sun, less than 1/10 as heavy. Its radius is about 16% of the Sun's radius, barely bigger than Jupiter though vastly denser. If you could somehow shrink the Sun down, you'd have to compress it to less than a sixth of its size to match Wolf 359 diameter. The surface temperature is around 2,800 degrees Celsius, cool by stellar standards, cooler even than most red dwarfs. It sits near the bottom of the main sequence, the faintest category of true stars. It emits less than a tiny fraction of a percent of the Sun's light, under 1/10,000th of the Sun's luminosity. If our star were a lighthouse blazing across the ocean, visible for miles in every direction, Wolf 359 would be a match struck in a storm, barely visible even from close range, a feeble flicker that barely penetrates the darkness. The star was discovered in the early 20th century by German astronomer Max Wolf, one of the first astronomers to truly embrace astrophotography as a tool for discovery. Wolf was a pioneer in using photographic plates rather than direct visual observation to study the sky, and he discovered hundreds of asteroids and many faint stars using this technique. He cataloged Wolf 359 in 1919, giving it the designation that bears his name. That number, 359, doesn't refer to its position in the sky or the order of discovery, but rather to its entry in Wolf's personal catalog of high proper motion stars, stars that showed noticeable movement across the sky over time. Despite being relatively nearby, despite being one of the closest stars to Earth, it remained mostly unknown outside professional astronomy circles for decades. No ancient astronomer ever saw it. No early telescope user ever noticed it. It played no role in human mythology or navigation. And perhaps that's part of its charm, part of what makes it interesting. It's always been here, close by in cosmic terms, hiding in plain sight yet completely invisible, a secret star that only revealed itself when we developed the technology to see it. From Earth, Wolf 359 sits in the constellation Leo, the Lion, one of the most recognizable constellations in the sky. Leo is prominent in both hemispheres, with its distinctive sickle shape and bright stars like Regulus. But Wolf 359 isn't one of those bright stars. It sits in an unremarkable part of the constellation, invisible to anyone looking at Leo's familiar pattern. It moves across the sky at a decent clip. Its proper motion is one of the higher ones known, about 4.7 arcseconds per year. That's not as fast as Barnard's star's record-setting speed, but it's still noticeable over years and decades. But because the star is so dim, Only precise instruments and careful comparison of photographs taken years apart can track its motion. It doesn't call attention to itself. It makes no show, no display. There are no dramatic outbursts, no unusual colors beyond its faint red glow, just a quiet, solitary existence burning hydrogen slowly in the darkness. A star like this, at the bottom of the main sequence, could live for trillions of years, silently fusing hydrogen in its core at a glacial pace, never reaching the dramatic end phases that larger stars face. There will be no red giant phase for Wolf 359, no planetary nebula, no supernova explosion. It will just slowly, very slowly, cool and dim over incomprehensible timescales. Eventually, far in the future, long after the sun has died, after massive stars have been born and exploded and been born again, Wolf 359 will fade to the point where it can no longer sustain fusion in its core. It will become what astronomers call a black dwarf, a cold, dark remnant of a star that has exhausted all possible sources of energy. But that won't happen for trillions of years, so long that it's essentially forever on human timescales. The universe isn't old enough yet for a single black dwarf to exist anywhere. Every red dwarf ever born is still shining, still fusing hydrogen, still in the prime of its extraordinarily long life. There's something oddly comforting about that kind of longevity, that kind of patient endurance. In a galaxy full of chaos, where massive stars explode violently, where planets collide and are destroyed, where black holes twist the very fabric of space and time, Wolf 359 simply endures. It's not flashy, not dramatic, but it's stable, reliable, a dim ember that's still burning quietly while everything else rushes and changes around it. There are no known planets orbiting Wolf 359, at least not yet. Astronomers have searched, of course, using the same techniques that discovered planets around Proxima and Barnard's star. They've scanned for wobbles in the star's motion that might indicate a planet tugging on it gravitationally. They've looked for dips in the star's light that might indicate a planet passing in front of it, transits that would reveal the presence of worlds crossing between us and the star. So far, nothing has turned up. No confirmed planets, no strong candidates waiting for additional data. That doesn't mean planets don't exist in the Wolf 359 system. It only means that if they do exist, they're small or distant or hidden in ways we can't yet detect with current technology. Red dwarfs are particularly tricky targets for planet hunting. Their small size and faint glow make precise measurements challenging. Any wobble caused by a planet is proportionally smaller. Any transit would cause a fainter dip in the already dim light. But in time, as telescopes improve, as spectrographs become more sensitive, as we accumulate years and decades of additional data, Wolf 359 might yet give up its secrets. Perhaps there are planets there, frozen worlds orbiting in the dim red light, or perhaps rocky planets hugging close to the star where temperatures might be more moderate. We simply don't know yet. And while Wolf 359 might be quiet scientifically, barely making waves in astronomical circles beyond its status as one of our nearest neighbors, it has managed to capture the imagination of many people through popular culture, especially in the world of science fiction and entertainment. Perhaps the most famous reference comes from the Star Trek universe, where the Battle of Wolf 359 became one of the most pivotal and devastating events in the series' lore. In that fictional story, a fleet of Starfleet vessels faces off against a deadly Borg cube near this very star and suffers catastrophic losses, with dozens of ships destroyed and thousands of crew members killed in a matter of hours. The choice of Wolf 359 as the setting for this battle wasn't random or arbitrary. The writers picked it precisely because it was a real star, close to Earth yet obscure enough that most viewers wouldn't have heard of it. It was the perfect place to stage something dramatic, a nearby location that felt threatening because of its proximity, yet mysterious because of its invisibility. So even in fiction, even in imaginative stories, Wolf 359 plays the role it seems born to play, the quiet, hidden threat, the darkness lurking close by that nobody notices until something happens. Back in reality, though, no such battles rage in this system. There's just hydrogen fusing quietly in the star's core, gravity holding everything together, and space stretching endlessly in every direction, silent and still. You could spend a lifetime orbiting this star and never see much change, never witness dramatic events. It would be a quiet existence, peaceful in its own way. A perfect place to hide if you wanted isolation, to think without disturbance, to observe the universe from a stable platform that will outlast almost everything else. If humanity ever sends probes this far, or even crewed missions one day in some distant future, it might not be because Wolf 359 has something dramatic or exciting to offer. It might just be the next logical step in expanding our reach, another node in the growing network of explored space. A stop along the way as we gradually push outward from our home star, visiting each neighbor in turn, mapping the local stellar environment one system at a time. There's one more thing that makes Wolf 359 fascinating beyond its faintness and proximity. And it's not something you see, but rather what it teaches us about the nature of our galaxy. Stars like Wolf 359 dominate the Milky Way numerically. Nearly 75% of all stars in the galaxy are red dwarfs, and many of them are even fainter than this one, even smaller, even harder to detect. If you could somehow catalog every star in the galaxy, you'd find that the bright stars we see in our night sky, the ones that form our constellations and capture our attention, are actually rare exceptions. The typical star is small, red, faint, and invisible without optical aid. Wolf 359 is far more representative of what stars are generally like than our Sun is. That has profound implications for our understanding of the galaxy and the search for life beyond Earth. If most stars are red dwarfs, and if red dwarfs can host planets as we now know they can, then most of the real estate in the galaxy exists around these faint stars. The habitable zones might be close to the stars, and the conditions might be challenging with flares and tidal locking, but the sheer number of red dwarfs means they could harbor most of the planets in the galaxy. As we slowly pull away from Wolf 359, leaving its faint light slipping into the backdrop of countless other stars, it's hard not to feel a sense of awe, not from what we've seen, because there wasn't much to see visually, but from what we haven't seen and what it represents. The star's very invisibility makes you wonder how many other stars we pass by every day without noticing, how many entire systems are drifting in the darkness just beyond our reach, waiting to be discovered. How many planets orbit these faint suns? How many worlds exist that we don't know about yet? The questions multiply the farther we travel from home. But the sky ahead is not all quiet and dim. Just ahead, piercing through the black like a cosmic spotlight, is something unmistakable, something impossible to miss. Something that doesn't hide in the darkness, but dominates it. It's brilliant, steady, unmissable, visible even through city lights, even on hazy nights. It's not just a star among many. It's the brightest star in our entire night sky, a beacon that has guided sailors and captured imaginations for thousands of years. We are now approaching Sirius, the dog star, the brilliant jewel of the constellation Canis Major. Look up from almost anywhere on Earth, on any clear night in the right season, and if you know where to look, you'll see it. The brightest star in the night sky, gleaming with an intense white light, piercing and beautiful. It's so bright that it sometimes seems to flicker with colors, blue and white and even hints of red, though that's usually just an effect of Earth's atmosphere making the light dance and shimmer. That's Sirius, our next destination, a star that couldn't be more different from Quiet Wolf 359. At first glance from Earth, it looks like a single brilliant point of light dominating the winter sky in the constellation Canis Major, the Greater Dog, which is why it's often called the Dog Star. But Sirius isn't one star. It's two, a binary system, a cosmic pair. One star alive and blazing with the intensity of youth, the other long dead and compacted into a dense remnant, a ghost of what it used to be. This is where we meet extremes in our journey, where we encounter both the bright and the dead sharing the same patch of space, bound together by gravity in an eternal dance. Sirius A, the component your eyes see from Earth, the brilliant light in the winter sky, is about twice the mass of the Sun and roughly 25 times more luminous. It pours out energy at a tremendous rate, far exceeding what our Sun produces. It shines with a brilliant bluish-white color, the signature of a hot star with a surface temperature close to 9,940 degrees Celsius. That's almost twice as hot as the Sun's surface, hot enough to shift the peak of its light output toward the blue end of the spectrum. It's only about 240 million years old, a baby by stellar standards. Our Sun, at 4.6 billion years, is nearly 20 times older. Sirius is still in the prime of its hydrogen-burning youth, still fusing hydrogen into helium at a furious pace in its core, still blazing with the intensity that comes from being a young, hot, massive star. If the Sun is a middle-aged engine pacing itself carefully to last billions of years, Sirius is a high-performance race car tearing through the track at maximum speed, burning its fuel quickly in a brilliant display of light and energy. But it won't last nearly as long as our Sun. Its life will be measured in hundreds of millions of years, perhaps a billion at most, not the 10 billion years our Sun can expect. That's the trade-off for burning so bright, for being so massive and energetic. You get a short, flashy existence followed by a dramatic end. Stars like Sirius will eventually exhaust their hydrogen fuel, swell into red giants, and then either explode or shed their outer layers, depending on their exact mass. The future is bright but brief. Now imagine, just for a moment, standing somewhere in the Sirius system, perhaps on a hypothetical planet orbiting at a safe distance. None are known to exist here yet, but imagine the possibility. Looking up at the sky, Sirius would blaze overhead so brilliantly that it would cast sharp shadows even at night, like a full moon but far brighter. The blue-white light would wash across the landscape, painting everything in cold, bright illumination. But not far away in the sky, if your eyes were sensitive enough, or if you had instruments to help you see, you'd catch sight of the system's strange companion, its dark twin. Sirius B waits in the shadows, orbiting its brighter companion. Sirius B is one of the most famous white dwarfs in existence, one of the first ever discovered, and one of the best studied examples of this strange type of stellar remnant. A white dwarf is what remains after a star much like our Sun, or even somewhat larger, runs out of fuel in its core, sheds its outer layers in a planetary nebula, and collapses under its own gravity. But Sirius B wasn't always small and compact. It used to be the larger, more massive star in the system. It was probably around 5 times the mass of our Sun originally, much larger than Sirius A. That means it lived fast and died young, following the pattern that massive stars always follow. After exhausting its nuclear fuel, probably just a few 100 million years ago, it swelled into a red giant, expanding to enormous size. Then it ejected its outer layers in a spectacular display, casting shells of gas into space. What remained was just the core, a sphere of carbon and oxygen no bigger than Earth, but containing nearly the entire mass of the original star compressed into that tiny volume. Now Sirius B is a dense, smoldering ember in space, extremely hot with a surface temperature of about 25,000 degrees Celsius, far hotter than the sun, but slowly cooling over time as it radiates away its residual heat. It no longer produces energy through nuclear fusion. Those days are long over. Instead, it simply radiates the heat left over from its former life, a fading echo of its glory days. It's small, just about the size of Earth, and dim when compared to its brilliant companion. It's utterly invisible to the naked eye from Earth, despite being in one of the brightest star systems in our sky. But it's there, orbiting Sirius in an elliptical path that brings it closer and farther from its companion over a period of about 50 years. The two stars are caught in a gravitational dance that's lasted for millions of years and will continue for millions more, bound together despite their vastly different natures. The bright young star and the collapsed remnant, eternally circling each other through the darkness. The existence of Sirius B was first predicted in the mid-1800s by German astronomer Friedrich Bessel, who noticed that Sirius seemed to wobble slightly in its motion across the sky. An invisible companion had to be tugging on it gravitationally, pulling it back and forth in a subtle way. Using mathematics and careful observation, he predicted that Sirius must have a companion star, even though nobody could see it. The actual discovery came years later, in 1862, when American astronomer and telescope maker Alvin Graham Clark spotted Sirius B visually for the first time. Using the largest refracting telescope of his era, a magnificent instrument he had built himself, he managed to glimpse the faint companion beside the brilliant glare of Sirius A. It was an extraordinary achievement given the difficulty of seeing a faint star next to such a bright one. The discovery was more than just a technical achievement or an interesting astronomical find. It opened an entire new chapter in astrophysics, fundamentally changing our understanding of stellar evolution. Here was proof that stars don't simply burn out and disappear when they die. They evolve through different stages, changing in dramatic ways, and they leave remnants behind. That idea, that stars have life cycles with different phases, eventually changed everything we thought we knew about the universe. It led to our modern understanding of stellar evolution, of how elements are formed, of how the universe has changed over billions of years. What's truly mind-bending about white dwarfs like Sirius B is their density, the amount of mass packed into such a small volume. You're looking at something with roughly the mass of our sun, all that matter, all those countless tons of material, crammed into a sphere about the size of Earth. The density is almost unimaginable. A single cubic centimeter of white dwarf material, a volume about the size of a sugar cube, would weigh over a ton, more than a small car. If you could somehow scoop up a teaspoon of material from Sirius B's surface and bring it to Earth, it would weigh more than a full-grown elephant. Several tons of matter compressed into a tiny volume. The only thing preventing the white dwarf from collapsing even further under its own immense gravity is something called electron degeneracy pressure, a quantum mechanical effect that kicks in when matter is compressed to such extreme densities. The electrons in the atoms are squeezed so tightly together that quantum mechanics says they can't be compressed any further. They push back with a pressure that has nothing to do with temperature, a purely quantum effect that supports the star against its own gravity. Sirius B is effectively a giant quantum object, a star-sized laboratory where physics operates at the edge of our understanding. Studying it helps us understand matter under extreme conditions, conditions we can never reproduce on Earth. But let's step back and remember where we are in human history and culture. Sirius isn't just a fascinating astrophysical system. For humans, for our species throughout history, it has always been more than just a star in the sky. It has myth, meaning, and history woven into our cultures. Ancient Egyptians noticed that Sirius rose just before sunrise at a particular time of year, just before the annual flooding of the Nile River. This heliacal rising, as it's called, became a crucial part of their calendar system. They built parts of their civilization around it, using it to predict the floods that brought fertile soil and allowed agriculture to flourish. To them, Sirius, which they called Sopdet, was a symbol of fertility, rebirth, and the annual cycle of renewal. The Greeks named it Serios, which means scorching or glowing, referring to its brightness, and the fact that it appeared in the sky during the hottest part of summer in the Mediterranean. They associated it with heat and drought. Even today, we use the term dog days of summer to refer to the hot period in July and August. The phrase comes from the fact that during this time in the northern hemisphere, Sirius, the dog star, rises and sets with the sun, appearing in the same part of the sky. Ancient peoples thought the combined heat of the sun and Sirius created the oppressive summer heat, though we now know that's not how it works. Many other cultures independently assigned great significance to Sirius. Aboriginal Australians incorporated it into their stories of celestial hunters. Polynesian navigators used it along with other stars for ocean navigation, guiding their voyages across thousands of miles of open water. The Dogon people of Mali have controversial and much debated claims about their ancient knowledge of Sirius B, long before modern telescopes could see it, though most scholars believe this knowledge came from modern contact, rather than ancient astronomical observation. Whether the stories are myth, coincidence, or misunderstanding, the fact remains that Sirius has always held human attention. It's too bright, too obvious, too prominent in our sky to ignore. Modern science hasn't lost interest either. The Hubble Space Telescope has captured stunning images of Sirius B, managing to separate it from its brilliant companion using advanced optics and imaging techniques. Ground-based observatories continue to track the binary dance of the two stars, refining our measurements of their orbits, masses, and properties. And future space missions will likely study the system more closely as we continue to improve our instruments and techniques. Finding planets in such a bright system would be a major achievement, a significant technical challenge. The glare from Sirius makes planet detection extremely difficult. Any planets would need to be found using indirect methods or with specialized coronagraphs that block the star's light. But if planets exist in the Sirius system, if worlds managed to survive the death of Sirius B when it went through its red giant phase, they would be fascinating objects to study. There's also a practical angle to Sirius's brilliance. Because it's so bright and close, it's used as a reference point in astronomical observations. Instruments are calibrated against it. Telescopes use it to fine-tune their optics. If our cosmic neighborhood had street lamps to light the way, Sirius would be one of the biggest and brightest bulbs, a beacon we can use to orient ourselves and our instruments. At a distance of about 8.6 light-years from Earth, Sirius is one of our closer neighbors, though not as close as the stars we visited earlier. It's prominent not because it's exceptionally close, but because it's genuinely bright, intrinsically luminous, putting out far more energy than our sun or the dim red dwarfs that dominate the neighborhood. As we begin to move away from this remarkable binary pair, drifting slowly away from the intense light of Sirius and the compact mystery of Sirius B, it's hard not to look back one more time. The light of Sirius will still be visible from Earth for millions of years to come, still shimmering through our planet's history books, still watched and wondered about and measured by future generations. But the farther we travel in our journey, the more distant it feels, not just in physical space but in character and tone. We're leaving behind the iconic stars, the ones that are easy to see from Earth, the ones that dominate our constellations and our mythology. Ahead lies another kind of star altogether, not famous in popular culture, not blazing in our night sky, but much closer to what makes up the bulk of the galaxy. We're heading now toward Ross 128, another red dwarf, another quiet star that tells a different kind of story. Ross 128 was discovered in 1926 by American astronomer Frank Elmore Ross, who was conducting a photographic survey of the sky looking for stars with high proper motion, stars that moved noticeably across the celestial sphere over years and decades. Ross 128 sits about 11 light-years from Earth, roughly 104 trillion kilometers of empty space separating us from this faint red ember. If you tried to travel there using the fastest spacecraft ever launched by humans, Voyager 1, it would take you over 200,000 years to make the journey, assuming you could somehow steer the probe in that direction and keep it functioning for all that time. And yet, astronomically speaking, 11 light-years is just down the block, close enough to study in detail, close enough to be considered part of our immediate neighborhood. Ross 128 is small, really small even compared to the other red dwarfs we've visited. It's just 17% the mass of the Sun, not much bigger than the smallest stars that can still sustain hydrogen fusion in their cores. Its diameter is about 20% of the Sun's diameter. If the Sun were a beach ball sitting on a table, Ross 128 would be barely bigger than a golf ball beside it. Its surface temperature is around 3,000 degrees Celsius, less than half as hot as the Sun's surface, giving it the characteristic red glow of cool stars. And its brightness is only about 0.036% of the Sun's total output, making it invisible to the naked eye, despite being relatively nearby in cosmic terms. In fact, if you could somehow replace the Sun with Ross 128 in our solar system, Earth would freeze solid almost immediately. The temperatures would plummet to hundreds of degrees below zero. The oceans would turn to ice. The atmosphere would begin to snow out of the sky as the gases condensed. Unless Earth was moved much closer to the star, it would become an uninhabitable frozen wasteland. That's the challenge with red dwarfs. They're small and cool, putting out very little energy, which means their habitable zones are extremely close to the star. But they're potentially very long-lived and steady, which is exactly what you want if you're hoping for planets with stable conditions where life might develop over billions of years. Now, here's where Ross 128 becomes genuinely interesting, where it transforms from just another catalog entry into one of the most important stars in our search for habitable worlds. In 2017, scientists confirmed the presence of a planet orbiting this quiet red dwarf. They designated it Ross 128b, and it immediately captured the attention of astronomers around the world. The planet is roughly 1.8 times the mass of Earth, close enough to Earth's mass that we can reasonably call it Earth-sized in the cosmic scheme of things. It's not a gas giant like Jupiter. It's not a mini-Neptune with a thick hydrogen atmosphere. It appears to be a rocky planet, a terrestrial world possibly with a solid surface you could theoretically stand on. But what made headlines worldwide, what generated excitement in the scientific community, wasn't just the planet's size and composition. It was where the planet orbits. Ross 128b sits in what astronomers cautiously describe as the potentially habitable zone, the region around the star where temperatures might, under the right conditions, allow liquid water to exist on a planet's surface. Let's pause there for a moment and really consider what that means. We have a calm, stable star. We have an Earth-sized rocky planet orbiting in the zone where water could be liquid. Suddenly, this quiet, unremarkable red dwarf starts to sound like one of the most promising places we've found yet to search for life beyond our solar system. Ross 128b completes one orbit around its star every 9.9 days. Yes, its year lasts less than 10 Earth days. That sounds extremely short, and it is. But remember, because the star is so dim and puts out so little energy, That short orbital period actually places the planet at just the right distance to receive similar amounts of energy to what Earth receives from our Sun. The planet orbits at a distance of only about 7 million kilometers from its star, 20 times closer than Earth is to the Sun. But because Ross 128 is so much fainter than our Sun, that close distance doesn't necessarily mean the planet is too hot. The calculations suggest it might receive a similar amount of stellar radiation to what Earth gets, placing it in that sweet spot. Not too hot that all water evaporates, not too cold that everything freezes solid. Just maybe, possibly right. But Ross 128 isn't just any red dwarf star. This is where the story gets even more interesting. It's unusually well-behaved compared to other red dwarfs we've studied. Unlike Proxima Centauri, which regularly lashes out with powerful flares that could strip away planetary atmospheres and sterilize surfaces with intense radiation, Ross 128 is practically polite by comparison. It's one of the quietest red dwarfs known. Observations show very little flare activity, very little variability in its light output. It just sits there burning hydrogen steadily and calmly, not causing trouble for any planets that might orbit it. That's tremendously important for habitability, because it means the planet, if it has an atmosphere, might actually be able to hold on to it over billions of years. Atmospheres mean atmospheric pressure, and pressure is what allows liquid water to exist on a surface rather than immediately boiling away into space or freezing solid. Without an atmosphere, you can't have liquid water. Without liquid water, life as we know it can't exist. So a calm, quiet star greatly improves the odds that a planet in the habitable zone might actually be habitable. There's more to the Ross 128 story, something strange that happened and briefly made this obscure star headline news around the world. In 2017, astronomers at the Arecibo Observatory in Puerto Rico, using that facility's massive radio telescope, detected mysterious signals coming from the direction of Ross 128. The signals were brief, unusual, and didn't match anything in the catalog of known interference or astronomical phenomena. For a brief, exciting moment, headlines buzzed with speculation. Could it be an alien radio signal? Was it a transmission from intelligent life orbiting Ross 128? Had we finally detected evidence of an extraterrestrial civilization? The scientific community urged caution, as they always do in such situations, but the public imagination ran wild for a few days. Reporters called it one of the best candidates yet for an alien signal. Social media exploded with speculation and theories. But as more data came in, as other observatories tried to confirm the signal, as scientists analyzed the characteristics more carefully, the most likely explanation emerged. The signal was probably from a geostationary satellite orbiting Earth, just routine interference from our own technology that happened to appear to come from Ross 128 direction due to the geometry of the observation. It wasn't alien. It wasn't a beacon from another civilization. It was just another example of how our own radio noise can sometimes fool us, especially when we're eager to find something extraordinary. Nothing to see here, as they say. Move along. But for a brief moment, Ross 128 was on the front page of science news worldwide, its name suddenly familiar to millions of people who had never heard of it before. And even without confirmed alien broadcasts, even without little green beings sending us messages, the system remains one of the most intriguing in our entire neighborhood. In fact, of all the potentially habitable exoplanets discovered near Earth so far, Ross 128b ranks among the very best candidates. Not because it's the closest, Proxima b is closer. Not because it's definitely Earth 2.0, we don't have nearly enough information to make that claim, but because it sits in a sweet spot combining multiple favorable factors. It's a stable, quiet star. It's a solid, rocky planet of reasonable size. It orbits in the habitable zone where liquid water might exist. And it's close enough to us that future observations might be able to tell us more about it, might be able to analyze its atmosphere if it has one, might eventually answer the question of whether it could support life. Ross 128 reminds us that not all stars need to make a dramatic show of themselves to be important. Some just keep burning slowly, quietly, reliably, minding their own business in the darkness. And in the long game of life and habitability, in the patient process that allows biology to develop and evolve over billions of years, that quiet stability might be the most important trait of all. Before we move on from Ross 128, it's worth taking a moment to appreciate just how fortunate we are to live in a time when we can know this much about stars we can't even see with our naked eyes. Stars that were completely unknown to anyone throughout human history, until recently. Ross 128 looks like nothing special through a telescope, just a faint red whisper on the edge of darkness, one dim point among millions. But thanks to high-precision radial velocity measurements that can detect wobbles smaller than a person walking, thanks to infrared observations that can peer through the darkness, thanks to decades of persistent data gathering and analysis, we now know its planet exists. We know the planet's mass to within a reasonable margin of error. We know its distance from its star. We know its orbital period down to fractions of a day. We even have preliminary estimates of what its climate might be like, what its surface temperature might be, though we haven't seen the surface directly and won't for many years to come. We've come remarkably far in a very short time, in just a few decades of intensive planet hunting, and we're only getting started. Now we keep going on our journey, because as quiet and promising as Ross 128 is, it's not alone out here. Out here in this stretch of space within about 16 light-years of our sun, we find a whole community of stars, a neighborhood, a collection of stellar systems that forms our immediate cosmic surroundings. Red dwarfs dominate the landscape, tiny points of slow-burning light scattered through an ocean of cold darkness. The local star neighborhood awaits, with dozens of systems we haven't examined in detail yet. Let's take a deep breath and pause for a moment in our journey. After drifting quietly past Ross 128 and its hopeful little planet orbiting in the habitable zone, after visiting bright Sirius and invisible Wolf 359, after examining each star individually, the space between stars begins to feel less like lonely darkness and more like the edge of a populated area. We've been treating each star like a separate island in the void, visiting them one by one, examining their properties and their planets. But now the perspective shifts slightly. We're no longer visiting isolated points scattered randomly through space. We're entering what astronomers call a cluster of sorts, a collective, a kind of natural district of space where stars are slightly more densely packed than average. This is our local star neighborhood, everything within roughly 16 light-years from the sun. And for the first time in our journey, instead of focusing intensely on just one or two stars at a time, we're going to glance around and see the whole street we live on, the whole community of stars that surrounds us. In this neighborhood, within this sphere of space 16 light-years in radius, you'll find around 50 star systems containing roughly 65 individual stars and brown dwarfs. That might not sound like a lot when you think about the hundreds of billions of stars in our galaxy, but that's actually the point. That's what interstellar space is really like. The Milky Way may contain hundreds of billions of stars, but even in what we think of as a relatively dense patch like our local neighborhood, it's still mostly empty space. Stars are separated by trillions upon trillions of kilometers of nothing. This is like finding a few scattered houses dotting a continent-sized wilderness of darkness. But these scattered stars, faint and distant as most of them are, each have stories of their own waiting to be discovered. Most of the stars in our neighborhood are red dwarfs, those tiny, cool, dim stars that can burn for hundreds of billions or even trillions of years, far longer than the current age of the universe. In fact, red dwarfs are not just common in our neighborhood. They're the most common type of star in the entire galaxy, making up roughly 70 to 75% of all stars that exist. But despite their overwhelming numerical dominance, none of them except the very closest and brightest are visible from Earth without a telescope. They're that faint, that dim, that easy to overlook. Out of all 65 stars and brown dwarfs in our local neighborhood, only a handful can be seen with the naked eye from Earth. And even those tend to be less impressive visually than spectacular stars like Sirius or the Alpha Centauri pair. The vast majority of our stellar neighbors are invisible ghosts, known only through telescopes and sensitive instruments. But just because they're quiet and invisible doesn't mean they're boring or unimportant. Far from it. Take Lytton 21,185, for instance. It's about 8.3 light-years away in the constellation Ursa Major, the Great Bear. It's one of the brightest red dwarfs in the sky, though that's not saying much since even the brightest red dwarfs are still too faint to see without optical aid. But Lytton 21,185, often called just Lytton star, is known for being one of the nearest stars with suspected planets. Astronomers believe it may host at least 2 super-Earths, rocky planets larger than Earth, but smaller than ice giants like Neptune. The evidence isn't conclusive yet. The signals are still being analyzed and debated, but the data suggests these worlds might exist. If confirmed, they would be fascinating targets for future study. And even if they don't turn out to be real, the star itself remains interesting as one of the fastest-moving stars in our sky after Barnard's star, racing through space at considerable velocity. Then there's 61 Cygni, a binary star system about 11.4 light-years away in the constellation Cygnus, the Swan. It's made up of 2 K-type orange dwarfs, stars smaller and dimmer than the Sun, but not quite as faint as red dwarfs. They orbit each other slowly, taking hundreds of years to complete one circuit. What makes 61 Cygni particularly special in the history of astronomy is its distinction as the first star beyond our solar system to have its distance measured using the parallax method. That groundbreaking measurement happened in 1838, accomplished by German astronomer Friedrich Wilhelm Bessel, and it was a monumental achievement for science. For the first time, humans could put a number on how far away the stars truly were. We moved from vague estimates and philosophical speculation to actual measurements, actual distances we could calculate and verify. It was proof that the universe was far vaster than most people had imagined, that even our nearest stellar neighbors were separated from us by distances that dwarfed anything in our everyday experience. The rapid motion of 61 Cygni across the sky, its high proper motion, earned it the nickname the Flying Star among 19th-century astronomers who marveled at how quickly it moved compared to other stars. No confirmed planets have been found orbiting either component of this binary system yet, but its quiet, stable nature makes it a plausible host for planetary families. The search continues. Epsilon Eridani is another local standout that deserves mention, another star that captures the imagination. It sits just 10.5 light-years away, making it one of our closest neighbors. It's a K-type star, an orange dwarf cooler than the Sun but warmer than most red dwarfs, and it has at least one confirmed planet orbiting it, possibly more waiting to be discovered. That confirmed planet is a gas giant similar in some ways to Jupiter, located relatively far from the star in a wide orbit. What makes Epsilon Eridani particularly fun and interesting, beyond the scientific data, is its prominent role in science fiction and popular culture. It's often included in stories about interstellar exploration and alien civilizations. In some versions of Star Trek lore, it's identified as the host star of the planet Vulcan, home to Spock's species, though different Star Trek productions have placed Vulcan at different stars over the years. The star is also relatively young compared to our Sun, only about 400 to 800 million years old, which means any planetary system around it might still be settling down, still being shaped by collisions and migrations. And yet Epsilon Eridani already shows evidence of structure in its planetary system. It has a wide dust belt similar to our Kuiper belt, the region of icy bodies beyond Neptune's orbit. That dust belt hints at a full and active planetary system, possibly with multiple planets that haven't been detected yet, possibly with debris left over from the formation process still swirling around the star. Another name that appears on lists of nearby stars is Gliese 1061, located about 12 light-years away. It's yet another red dwarf, one of the many that populate our neighborhood. Only recently has it entered the broader exoplanet conversation, beyond specialized astronomical circles. Observations suggest that 3 planets may orbit this quiet red star. One of them, designated Gliese 1061d, appears to sit in the star's habitable zone based on its orbital distance and the energy it receives from its star. But remember, and this is important to keep in mind, the habitable zone is just a rough estimate based on temperature. It only means a planet could theoretically have the right temperature for liquid water to exist on its surface. It doesn't tell us anything definitive about whether the planet actually has an atmosphere, what that atmosphere might be made of, what the surface conditions are really like, or whether it's actually habitable in any meaningful sense. A planet can be in the habitable zone and still be completely inhospitable to life for dozens of different reasons. But being in the habitable zone at least puts it on the map as worthy of further investigation, as a target for future observations. And that's becoming the theme as we look around our neighborhood. You look at the catalog of nearby stars, and it seems like every 3rd or 4th star has a planet candidate being studied, has signals in the data suggesting possible worlds orbiting in the darkness. Many of these planets don't get much press attention, don't make headlines, because they're orbiting faint stars nobody's heard of, and their properties haven't been studied in enough detail yet to say anything definitive. But give it time. Over the next few decades, as new observatories come online and existing ones continue gathering data, we'll learn more about these worlds. The James Webb Space Telescope, already operational and returning stunning data from across the universe, might give us atmospheric spectra of some of these planets. Future ground-based observatories like the European Extremely Large Telescope, currently under construction, will have the resolution to directly image some of these worlds. And missions still in the planning stages, concepts with names like LUVOIR or HAB-X, might one day give us the first hints of biosignatures, chemical signs in a planet's atmosphere that could indicate the presence of life. Imagine detecting oxygen and methane in the atmosphere of a planet orbiting one of these nearby stars, gases that on Earth are produced primarily by living organisms. It wouldn't be proof of life, but it would be tantalizing evidence worthy of intense follow-up study. Now, it's important to understand just how this little bubble of space around our sun is structured, what it actually looks like if you could see it from outside. If you could somehow travel far away, say 100 light-years from the sun, and then zoom back in to look at the 16 light-year radius around our star, you'd see something interesting. You wouldn't see a spiral arm of the galaxy or a dense star cluster. You wouldn't see nebulae glowing with the light of star formation. You'd just see individual pinpricks of light, points of fusion-powered matter scattered in 3-dimensional space, spread throughout a roughly spherical volume. It's quiet still, and in its own way kind of beautiful in its simplicity. The distribution isn't perfectly uniform. Some directions have slightly more stars than others just by chance. Some stars are close together, forming binary or even triple systems like Alpha Centauri. Others are isolated, alone in the darkness. But overall, it's a relatively sparse, calm region of the galaxy. We don't live in a particularly crowded or active area, just a typical suburban region of the Milky Way. If interstellar travel ever becomes possible, even just with robotic probes in the near term, or perhaps with crewed missions in some distant future we can barely imagine, this local neighborhood would be humanity's playground for the first few centuries of exploration. We'd have dozens of targets within reach, dozens of systems to explore and study in detail. We might build relay stations to boost communication signals across the light years. We might establish scientific outposts on planets or moons where conditions allow. We might send scouting probes to every system, mapping them in detail, cataloging their planets and asteroids and comets. Each star would become a kind of port in the darkness, a waypoint connected to others by long, slow beams of data, and occasional spacecraft making the journey. That's what makes the local star neighborhood feel so intimate, so manageable. It's not the whole galaxy, not the millions of stars that make up our spiral arm. It's just our street, our immediate surroundings, the stars we might realistically reach if we ever develop the technology and will to make the attempt. And just think about this for a moment. This neighborhood we've been exploring, this collection of about 50 star systems, is only an infinitesimally tiny slice of the galaxy. It's a single dandelion seed's worth of stars in a storm of hundreds of billions. Our local bubble occupies only about 32 light-years in diameter, while the Milky Way stretches 100,000 light-years from edge to edge. If the galaxy were a continent, our neighborhood would be smaller than a single house, a tiny room in an enormous mansion. And yet, for now at least, it's ours. Our street, our cluster, our beginning point for understanding the stellar universe around us. And now, we're approaching our final major destination on this leg of the journey through nearby space. We're about to visit a system that sits just on the edge of what we might call truly near, a place that rounds out our tour and gives us one more reason to keep looking outward with hope and curiosity. At just over 20 light-years away, roughly 190 trillion kilometers from home, we arrive at a destination that once stirred headlines and sparked imaginations like few other stars had before. This is Gliese 581, a red dwarf that became one of the most talked about stars in the entire night sky for a brief, exciting period. Gliese 581 sits in the constellation Libra, the scales, visible from the southern hemisphere. It's a red dwarf star, cooler and dimmer than the Sun by a very large margin, emitting only about 1% of the Sun's total light output. You can't see it with the naked eye, wouldn't know it was there without a telescope. But in 2007, Gliese 581 became suddenly famous, its name appearing in newspapers and on television news broadcasts around the world. Because around this quiet reddish glow, clinging to this unremarkable star, were planets. Not just gas giants like Jupiter orbiting far from their star, and not just scorched rocks too close to be habitable. There appeared to be something different orbiting Gliese 581, something that for a time seemed tantalizingly close to Earth-like conditions. Let's start with the star itself, the anchor of this system. Like most red dwarfs we've encountered, Gliese 581 is small compared to our Sun. It's only about a third the mass of the Sun, and just over a third its radius. If you could line them up side by side, the Sun would dwarf Gliese 581, making it look tiny and insignificant by comparison. Its surface temperature is relatively chilly at 3,200 degrees Celsius, much cooler than the Sun's 5,500 degrees. That cooler temperature shifts its light output toward the red and infrared parts of the spectrum, making it glow with that characteristic dull red color that defines red dwarf stars. But here's what astronomers love about Gliese 581. It's old, stable, and fairly quiet compared to some red dwarfs. It doesn't show the kind of violent flare activity that makes stars like Proxima Centauri so potentially hazardous to any orbiting planets. A star like this can live for tens of billions of years, possibly 100 billion years or more, providing an incredibly long window of opportunity for planets to evolve, for atmospheres to develop, for climates to stabilize, and maybe, just maybe, for life to emerge and flourish over timescales that dwarf the entire history of our solar system. Now the planets. At least 4 have been confirmed with reasonable confidence, orbiting Gliese 581, though some claims of additional planets have been disputed and remain controversial. But the real story here, the reason Gliese 581 became famous, revolves around one particularly controversial world that may or may not actually exist. Back in 2010, a team of astronomers led by Stephen Vogt and Paul Butler announced that they had found a planet they called Gliese 581g. And this wasn't just another exoplanet to add to the growing catalog. This was potentially something extraordinary. It was described as an Earth-sized planet orbiting right in the middle of the habitable zone of its star, possibly the most Earth-like planet ever discovered up to that point in history. The planet was estimated to be about 3 to 4 times the mass of Earth, making it a super-Earth, but still in the range where it might have a solid surface rather than being a gaseous mini-Neptune. Its orbit placed it at a distance from Gliese 581, where temperatures could theoretically allow liquid water to exist on the surface, that magical condition that seems essential for life as we know it. The team that discovered it nicknamed the planet Zarmina's World after the wife of one of the discoverers. Artists created renderings imagining what the planet might look like. Rocky terrain, possibly oceans, clouds swirling in an atmosphere, all bathed in the reddish light of its small sun. It felt close, real, maybe even reachable one day in some distant future. The possibility that this could be a world where life existed, where evolution might have created alien biology, was tantalizing beyond words. News media around the world picked up the story. Headlines proclaimed the discovery of a potentially habitable planet. Scientists gave interviews about the implications. The public's imagination caught fire with the idea that we might have found another Earth, or at least something approaching it, just 20 light-years away. But the celebration didn't last long. Science requires verification, requires confirmation from independent teams using independent data. And when other astronomers looked at the same data, when they tried to confirm the signal that supposedly revealed Gliese 581g, they couldn't see it clearly. Follow-up studies cast serious doubt on the planet's very existence. Some astronomers believed that the signal interpreted as a planet was actually just statistical noise, random fluctuations in the data that happened to look like a planetary signature, but didn't represent a real object. Others suggested it might be the result of stellar activity, variations in the star's own behavior being misread as the gravitational wobble caused by a planet. For years, the debate went back and forth in scientific journals and conferences. Is Gliese 581g real or not? Does it exist, or was it a mistake, an artifact of insufficient data or over-eager interpretation? Teams analyzed and reanalyzed the observations, added new data, tried different analysis techniques. Some researchers remained convinced the planet was real. Others were equally convinced it wasn't. Today, After more than a decade of additional observations and analysis, most of the astronomical community leans toward skepticism. The consensus view is that Gliese 581g is probably not real, or at least not detectable with our current instruments and methods. The signal that suggested its presence has not been consistently reproduced. It may have been a statistical fluke, or the star's own variability creating a false positive, or simply an overinterpretation of noisy data. And yet, even though Gliese 581g itself appears to be more wishful thinking than reality, the system still holds other planets that are definitely real and still quite interesting in their own right. The story of Gliese 581 didn't end with the disputed planet G. Other worlds in the system remain confirmed and worth studying. Gliese 581c, for instance, is definitely real. It's about 5.5 times the mass of Earth, making it a substantial super-Earth. It orbits much closer to the star than the disputed Gliese 581g, at a distance where it probably receives too much stellar radiation to be comfortably habitable. Surface temperatures are likely too high for liquid water, probably making it more like a super-Venus than a super-Earth in terms of conditions. But it was once considered a strong candidate for habitability in the early days of exoplanet science, before we understood as much as we do now about how habitability works around red dwarf stars. The discovery of Gliese 581c in 2007 was actually what first brought this system to widespread attention, before the controversial discovery of planet G. The system as a whole has become something of a textbook case in exoplanet science, an example that teaches important lessons. It showed how extraordinarily difficult it is to confirm Earth-sized planets, especially using indirect detection methods like radial velocity. It demonstrated how easy it is to overstate a discovery when the data is marginal or ambiguous. It reminded everyone that extraordinary claims require extraordinary evidence, and that science works through verification and skepticism, not through hoping something is true. But the Gliese 581 story also showed how thrilling the process of planetary discovery can be, how exciting it is when we think we might have found something extraordinary. The attention the system received, even though one of its planets turned out to be probably not real, helped change the public's imagination around space exploration and the search for habitable worlds. It made people believe, even if only briefly, that we might be on the verge of finding a second Earth. It made the search for life beyond our solar system feel real and immediate and possible. And even though we haven't found that perfect Earth twin yet, the excitement was justified. We're living in the era when humanity is finally able to detect and study planets around other stars, something that was pure science fiction just a few decades ago. We're still many decades, maybe centuries away from getting definitive answers about whether any planets in the Gliese 581 system or any other nearby system could support life. We need better instruments that can directly image planets rather than just detecting them indirectly. We need spectroscopy powerful enough to analyze the chemical composition of exoplanet atmospheres. We need the patience to accumulate years and decades of additional data. But the beauty of Gliese 581, the reason it remains important despite the disappointment about planet G, is that it reminded us what's possible. It pushed the boundaries of exoplanet detection, showing how far our technology has come and how much farther it needs to go. It demonstrated how fragile and subtle the signals from small rocky planets can be, teaching us that we need to be careful and rigorous in our analysis. And it showed how far humanity is willing to go in the search for other Earths, how persistent we are in trying to answer the ancient question of whether we're alone in the universe. Even if none of the planets orbiting Gliese 581 turn out to be truly habitable, The system itself was a catalyst that advanced the science and captured millions of people's imaginations. There's another layer to the Gliese 581 story worth mentioning, one that adds another dimension to this star's connection to humanity's reach into space. Gliese 581 was one of the first stars to receive a purposeful, deliberate broadcast from Earth, a message sent intentionally toward another star system. In 2008, a message called A Message from Earth was transmitted using the RT-70 radio telescope in Yevpatoria, Ukraine. The message contained 501 text messages, photos, and drawings selected from submissions by people around the world through a social networking website. It was humanity reaching out, saying hello to the cosmos, choosing this particular star as one of our early attempts at interstellar communication. The radio signal, traveling at the speed of light, will arrive at Gliese 581 in the year 2029. If anyone or anything is out there listening, if there are beings with radio telescopes pointed in the right direction at the right time, they'll receive our message. They'll know that on a distant planet orbiting a yellow star, there was a civilization that looked up at their sun and wondered. That's both thrilling and eerie when you think about it. This is one of the very few stars we've ever intentionally reached out to in that way, one of the handful of targets for humanity's early attempts at messaging extraterrestrial intelligence. Whether anyone will ever receive it, whether anyone is there to receive it, we don't know and may never know. But we sent it anyway, because the possibility was too compelling to ignore. And so Gliese 581 stands at the edge of our journey through the local stellar neighborhood. Not just the edge in terms of distance, sitting 20 light-years away at the outer boundary of what we call nearby, but the edge of our hope, our caution, and our curiosity about what's out there in the darkness. It marks a turning point where our journey through familiar space starts to fade into the unknown. Beyond this distance, the signals from planets grow weaker, harder to detect. The travel times grow longer, making even conceptual missions more challenging. The dream of visiting, of sending probes or perhaps one day even astronauts, becomes more distant and speculative. Yet even at 20 light-years, what astronomers still consider nearby in the grand scheme of the galaxy, Gliese 581 holds onto our imagination. It reminds us that searching for habitable worlds, searching for life beyond Earth, isn't about certainty or guaranteed success. It's about possibility, about the drive to explore and understand. It's about building better instruments, running the calculations more carefully, dealing with disappointments when a promising discovery doesn't pan out, and still coming back the next day to try again with renewed determination. It's about the long, patient work of science, the accumulation of knowledge piece by piece, even when the answers we seek remain frustratingly out of reach. From here, as we look outward from Gliese 581 toward more distant stars, our map of local space begins to thin out considerably. The next stars are farther away, harder to study in detail, often less well known because the light from any planets is even fainter, the signals even more subtle. The neighborhood we've been exploring, this comfortable sphere of space within 20 light-years, starts to give way to the broader galactic environment. But we'll always remember this journey, this tour from Proxima to Gliese 581 and all the stars in between. These quiet, dim local stars stretch across space like forgotten embers scattered through the darkness, each one a world unto itself, each one potentially hosting planets we haven't found yet. They are the ones closest to us in the vast galaxy, the ones we'll likely reach first if we ever develop true interstellar travel capability. They're the ones that, in the cold silence of space, still whisper the possibility that we might not be alone, that somewhere in the darkness around one of these stars, life might have found a way to emerge and persist. The journey we've just completed feels immense when you really think about it. when you let yourself absorb the full scope of what we've seen. We've drifted more than 20 light-years from the sun, visiting stars that range from glowing giants like Sirius to barely visible red dwarfs like Wolf 359, from the violent and volatile like Proxima Centauri to the quiet and hopeful like Ross 128. We've examined double stars dancing around each other. We've studied dead stellar remnants like the white dwarf Sirius B. We've looked at planetary candidates in habitable zones. We've considered the possibility of worlds where water might flow and life might exist. We've traveled across distances that would take our fastest spacecraft tens of thousands of years to cross, examining cosmic environments that humans will likely never visit in person. But here's the striking part that puts everything in perspective. Despite all we've seen, despite all we've imagined, despite all we've marveled at, we've barely scratched the surface of what's out there. We've barely begun to explore. The stars we've visited so far, every single one from Proxima to Gliese 581, all lie within a region that astronomers call the local neighborhood or the solar neighborhood. That sounds cozy when you first hear it, doesn't it? It sounds intimate, manageable. Like we're talking about a cluster of familiar houses on a friendly street in a small town where everyone knows each other. And in a way, on a cosmic scale, that's exactly what it is. All these stars, Proxima Centauri sitting just over 4 light-years away, Sirius blazing at 8.6 light-years, Ross 128 at 11 light-years, all of them sit within just about 20 light-years of the Sun. That's a bubble, a sphere of space only 40 light-years wide in diameter. It's our immediate surroundings, our front yard in the cosmic scheme of things. Now picture this, and really try to visualize the scale. The Milky Way galaxy, our home galaxy, the great spiral of stars we're embedded within, is roughly 100,000 light-years across from edge to edge. If our journey so far were a walk through a city, if the galaxy were an urban landscape we were trying to cross, we haven't even left our front yard yet. We haven't reached the end of our driveway. Our galaxy isn't just big in some abstract way. It's staggeringly, incomprehensibly vast beyond what our minds are really equipped to grasp. There are more than 100 billion stars scattered across its spiral arms, maybe as many as 400 billion depending on how you count them. That's more stars than there are grains of sand on many beaches, more than there are trees on Earth. Some of those stars are gathered in tight clusters, where hundreds or thousands of stars orbit in close proximity. Others float alone in vast stretches of empty space, isolated for dozens of light-years in every direction. Some are young, just millions of years old, still surrounded by the disks of gas and dust from which they formed. Others are ancient, nearly as old as the universe itself, having burned steadily for over 13 billion years. And as we float here at the outer edge of what we call the nearby neighborhood, at the boundary of the region we've been exploring, the view stretches beyond measure when we look outward. Our galaxy is waiting out there in the darkness, spiral arms full of stars we haven't cataloged, nebulae where new stars are being born, regions we've barely studied except as distant smudges of light. One day, maybe far in the future, maybe farther than we can currently imagine, we'll leave this neighborhood for good. We'll develop the technology to travel faster, to journey farther, to endure longer voyages. We'll build ships that can cross dozens or hundreds of light years, perhaps using methods we haven't invented yet, physics we don't fully understand yet. We'll visit stars that today are just catalog numbers and coordinates in astronomical databases. Stars so far away we haven't even attempted to search them for planets yet. We'll probe deeper into the spiral arm, exploring regions of space where the density of stars increases, where massive stars are more common, where the environment is more energetic and dynamic. We'll decode the atmospheres of distant exoplanets using spectroscopy, breaking their light down into component wavelengths and reading the chemical signatures like fingerprints. We'll listen more carefully for signals, for any sign of technology or intelligence, expanding our search for extraterrestrial civilizations beyond our immediate neighborhood. And perhaps we'll send more messages of our own, broadcasting toward promising star systems, letting the galaxy know that here, around this particular yellow star, intelligence emerged and looked outward with wonder. Maybe we'll even receive answers, replies from civilizations we haven't imagined yet, confirmations that we're not alone in the vast darkness. Maybe, in some distant future we can barely conceive of, we'll find another blue world under another sun, a planet with oceans and continents, with an atmosphere you could breathe, with life that evolved independently from Earth's biology, a place where evolution took a different path, but arrived at similar solutions, creating a biosphere as rich and complex as our own. But every long journey begins somewhere. Every great exploration starts with those first tentative steps into the unknown. And our journey, humanity's first steps toward the stars, began right here with this tour of the stars closest to us, the immediate neighbors we've been visiting one by one. They are few in number, this collection of 50 or so star systems, but they are critically important for our understanding of the galaxy and our place in it. They anchor us in space, giving us reference points by which we can measure greater distances. They provide nearby laboratories where we can study stellar physics, planetary formation, atmospheric dynamics, all the processes that happen around stars throughout the galaxy. They point the way forward, showing us what kinds of stars exist, what kinds of planets orbit them, what conditions might allow for habitability and life. So now, as we prepare to zoom out from this little bubble of space, as we shift our perspective to look again at the Milky Way in its full majesty, we can start to place ourselves in the proper context. We can see where we sit in the Great Spiral, in one of the outer arms orbiting about 26,000 light-years from the galactic center. We can appreciate how small our neighborhood really is compared to the whole, how much more there is to explore, how many mysteries remain unsolved. We are small, there's no denying that. Our sun is one star among hundreds of billions. Our Earth is one planet among countless trillions that probably exist throughout the galaxy. Our entire civilization, our entire history, has played out in a tiny corner of one spiral arm of one galaxy among hundreds of billions in the observable universe. But we are not insignificant. We are not meaningless. We are the part of the universe that woke up and became aware of itself. We are matter organized in such a way that it can contemplate its own existence, can ask questions about its origins, can seek to understand the cosmos from which it emerged. We are explorers, driven by curiosity that seems to be hardwired into our species. We look up at the night sky and wonder what's out there, and then we build telescopes to find out. We imagine traveling to other stars, and then we design missions to make it possible. We dream of finding life beyond Earth, and then we devote careers to the search. And the stars we've been visiting, these neighbors in the darkness, are not just abstract points of light to be cataloged and measured. They are destinations, real places we might actually reach someday. They are the stepping stones to the greater galaxy, the first waypoints on a journey that might ultimately take us across the spiral arm and beyond. The neighborhood we've explored is just the beginning of something vast. It's the preface to a story that will take thousands of years to unfold, the introduction to an exploration that might occupy humanity for the rest of our existence as a species. As our technology improves, as our instruments become more sensitive, as our theoretical understanding deepens, we'll discover more planets around these nearby stars. We'll find smaller worlds we couldn't detect before. We'll characterize atmospheres, measuring their chemical compositions and looking for signs of habitability or even biology. We'll map the architecture of these planetary systems, understanding how they formed and evolved. We'll answer questions we don't even know how to ask yet. And eventually, if we survive our current challenges, if we learn to work together as a species, if we maintain our drive to explore and understand, we might send emissaries to these nearby stars. Perhaps small robotic probes at first, traveling for decades to reach the nearest systems and send back data. Later, maybe larger missions with more sophisticated instruments, capable of detailed study and even sample return. And who knows, in some future century or millennium, perhaps crewed missions will venture to the nearest stars. Perhaps humans will walk on planets orbiting Proxima Centauri or Alpha Centauri, will establish settlements under alien suns, will look up at night skies where our sun is just another star among many. It's a long road ahead, longer than any journey humanity has ever attempted. But it's a road that begins right here, right now, with these first tentative explorations of our local stellar neighborhood. Every star we've visited on this journey has taught us something. Every planet discovered has expanded our understanding. Every measurement, every observation, every careful analysis contributes to the growing body of knowledge that will one day make interstellar exploration possible. So we conclude our journey here, at the edge of the familiar, looking outward toward the unknown. We've traveled from the sun through a small sample of the stars that surround us, visiting bright giants and dim dwarfs, examining planetary systems and stellar remnants, marveling at the diversity of what exists even in our small corner of the galaxy. The stars are waiting. The galaxy is vast. The universe is full of wonders we haven't imagined yet. And we, small and temporary as we are, carry within us the spark of curiosity that drives exploration, the desire to know what lies beyond the next horizon. The journey continues, always outward, always deeper into the cosmic ocean. And though we may never live to see the day when humans walk among these distant stars, we can still dream, still wonder, still look up at the night sky, and know that each point of light is a sun like ours, possibly with worlds of its own, possibly with stories waiting to be discovered. Good night, travelers. Rest well, and dream of stars.